Hello. Good morning. We are starting in a minute. Please take your seats. Good morning, everyone, and welcome to ICFP and SPLASH 2025 in Singapore. It's, hey. I'm so happy to see so many people made it here. We are going to grow even bigger towards the later part of this week. As some of you know, my name is Bialgebraic. I'm an associate professor at NUS, and I'm the general chair for ICFP and also the local chair for this entire event. So a few things about the logistic information. I won't take much of your time because I'm really excited to hear our first keynote speaker. So this week, we have, and I counted 30 collocated events happening throughout 7 days. So this is the day 2, and we are now at Marina Bay Sands Convention Center, staying here for the rest of the week. This is the venue. You can find the same map at the registration desk. This is what it will look like for the first 3 days. And then the Plenary West will be split into 2 more rooms for Thursday to Saturday. We are now in Orchid Plenary, and it's going to get quite full later this week. And we will also have the streaming in Orchid West. The lunches will take place in Orchid Dining Hall. There is some part of it allocated for seating, and some part of that are the cocktail tables, and there are also cocktail tables by the garden walk, where we have a beautiful view, so you are welcome to have lunch there and enjoy it and just walk around. And in Plenary Dining, we will have the space reserved for the DI and mentoring lunches. Okay, so a few things. So, okay, this is where we will get the streaming. Additionally, if you want to have a research meeting during the week, so we have a meeting room. There should be a QR code on it, which allows you to book it, so in case if you want to have it. We are on the 3rd floor. It's actually quite convenient because if you follow this path, you will see that you can exit to the Sky Bridge and go through the Marina Bay Sands Hotel, the 3-tower building, directly to the gardens by the bay. And if you are tired or too cold to sit in one of these rooms, this is something that you might consider doing. So we are sharing this space with a few other conventions, so please wear your badge so we could identify you and let you to the lunch space. And yeah, so if you forget it, well, you can find me and I'll try to identify you. If you're a person, this is the hashtag. This is the schedule of the social events that we are going to have, quite a few. Tonight and on Thursday, we will have the welcome receptions for ICFP and SPLASH correspondingly. That will also be combined with the poster and student research competition poster sessions. And importantly, in the dining room, we will have the photo booth installed, which will print pictures of you on the fridge magnet. So you might want to check it out. You don't need to wear this dress. This is the stock image. On the reception, we have a few free tickets to give away. We have tickets to the Gardens by the Bay Observatory, so to go to one of these super trees, and also to redeem an experience like going to an aquarium in Sentosa. We don't have as many tickets as we have the attendees. We have about 700, and 300 we will release today and more later this week, so please grab yours and enjoy. So we will have another hike on Sunday. I've been told that the one on Saturday was quite a bit of fun. Many people showed up. And other than that, we've put together a list of things to do in Singapore, so we hope you enjoy. Speaking of which, so we have Lau Pa Sat Hawker Center in just 15 minutes walk from here. This is where you might want to have dinner. It's a really nice location. We also can see the Merlion directly from the hallway track. It's here across the bay. And here are the gardens by the bay. So this is a large convention, and I have to remind you, well, to be civil, and we have the code of conduct in place that obviously means that, well, no any bullying or harassment or anything of that kind will be tolerated, but that hopefully will not be a problem. One thing that I want to emphasize is that since many people are new to the conference, when you having discussions during the hallway track, try to follow the Pac-Man rule. So make a circle with a slice open in it so people could jam in and introduce themselves and have a nice conversation with you. And finally, if there is something that makes you unhappy that you want to report, we have sick plan cares, and we have many of the members of the sick plan cares on site. This is the whole committee, and these people will be present during the conference. So if you have anything that you would like to discuss with them, find them or let me know. I'll find them for you. And with this, I hope you will enjoy the conference. Thank you very much.
Hi, everyone. Oh, that's a little loud. Great. So hi, I'm Derek Dreyer, and I want to thank the organizers for letting me have a few minutes this morning right before the invited talk to give you some news about the Journal of Functional Programming, JFP. So as many of you may know, JFP is one of the leading journals in programming languages since '91. Currently, myself and Gabby Keller are the editors-in-chief. And JFP has a long-standing relationship with ICFP. So there is actually two sort of directions this goes. One is the journal first papers. You'll see in the program, I think there are around 9 journal first papers that will be presented at this year's ICFP. So these are papers that were submitted and published in JFP, and then the authors get to give a talk at ICFP if they want. And that's intended for fresh journal submissions. And then the reverse direction is we also have regular extended sort of special issues of JFP for extended versions of conference papers from different years of ICFP. In the last couple of years, we've also been extending this to special issues for other conferences like Popl and Uppsala as well. So why am I talking to you this morning? It's not just to give you an ad for JFP. Oh, and one more bit here is just that it's JFP has actually been gold open access since 2022. So yeah, the point of the reason I'm here is to tell you about some big news that's happening with JFP. So there's sort of the good news and the bad news. So I'll start briefly with the bad news. The bad news is that Cambridge University Press informed us last year, or the end of last year, that they are dropping JFP along with several other journals that they own by the end of 2025 for a variety of reasons. Not because of the performance of JFP, so to speak. We've actually had an increase in the number of submissions in the last couple of years, but for other reasons. So the good news is that they have also offered to transfer ownership of JFP to the editors. And so that's actually, perhaps there's a real silver lining here, which brings me to the good news. And the good news is that we are currently in the process of acquiring ownership from Cambridge University Press and transferring to a different publication model, hopefully, we expect, through EpiSciences. This is not quite done yet, but hopefully will happen in the next couple months. And the upshot of this is that, as a result, JFP will actually become a Diamond open access journal. That means there will be no fees for anyone, for authors or readers. Papers will be published as basically an overlay on archive, probably. And we also expect to still maintain the Claravit indexing of the journal, which is very important to many of our authors. A side benefit of this, in addition to Diamond Open Access, which I think is already a very big deal, is that we'll also have some more freedom and control over various aspects of the journal, including things like the style file, which is pretty out of date, which we would like to make more compatible with, for example, the PAC&PL style file. And we can also experiment with other types of articles and so forth. So we'll have ownership of the journal in the hands of the researchers who actually work in this area. What does this mean for you, and why am I speaking to you right now, other than just to give you this mostly good news? The reason is we need your help. Okay, so first of all, during there's going to be a sort of difficult transition period, of course, when you're moving to a different publication system, et cetera. So please keep submitting to JFP. Okay, for now, right now, that you can still submit through the Cambridge University Press interface, the Manuscript Central site, as before. But soon, this is going to be, we believe, through EpiSciences. And we will announce when that transition actually happens, and CUP will will redirect authors to the EpiSciences website. In addition, it's going to be there's going to be some growing pains when we do this transition. So we would request help from the community. First of all, be patient during the transition. It's going to take a little time, and we're all researchers who have day jobs, so We're doing our best. Authors of papers that are in flight currently will probably need to resubmit them to EpiSciences, but that's, again, not going to be that big a deal. What we really do need help is volunteers to help with the transition, with supporting layout editing for papers under the new submission system, and with moving the website over and making our own website for the new JFP. So if you're interested in doing this and you want to support the continued and we hope improved development of JFP, please contact me or Gabby Keller or Jeremy Gibbons, who's a former editor-in-chief who's been helping us out a lot. Gabby and I will be here at the break after this session, so if you want to talk to us and ask us any questions, please go ahead. Thank you very much. Actually, yeah, good. So it's also my pleasure to introduce our first speaker of the conference. Yeah, you can get set up. So yeah, it's my pleasure to introduce Satnam Singh. Satnam is a long-standing, card-carrying member of the functional programming community, dating back to its early days as a PhD student under the supervision of Mary Sheeran at Glasgow in the late 80s and early 90s. Satnam has worked on many different problems, but broadly speaking, his main research focus has been on developing functional programming-based tools for hardware design and verification. He has spent time at a range of different companies, including Xilinx, Microsoft, Facebook, Google, and Grok, during which he has made important contributions to the core technology underpinning the main commercial tools for hardware verification. These include his work on Lava, a DSL for hardware design and formal verification, as well as his recent work at Google and Grok on using functional programming to accelerate algorithms running on specialized machine learning chips. He also received the most influential ICFP paper award in 2019 for his pioneering work on concurrency and parallelism in Haskell. And last but not least, on a personal note, I can say he is an amazing cook. So if he ever offers to cook for you, just say yes. Okay? So please join me in welcoming Satnam Singh.
Thank you for the kind introduction, Derek. Good morning. I love functional programming, and I really love functional programming for designing hardware. So I'm going to celebrate various ways of doing functional programming. Let me get myself sorted out. Oh, there we go. So machine learning chips, they're used to accelerate inference and training. And some of the hottest commodities on the planet, quite literally. And recently there was this deal between OpenAI and AMD about swapping equity for chips in some kind of complicated manner. These things are so valuable, the deals for them done at nation-state kind of nation-state levels. So the design of these chips is like a super important thing in the world, and I think we should care about them. I've worked on the design of 2 machine learning chips. These things are called like tensor processing units. This is an early one from Google. And I also worked on one at a company called Grok as well. And these chips help to especially make inference tasks go much, much faster than running on a processor. And the main competition are GPUs from NVIDIA. The one that you saw at Google, the one I worked on there with Leonard in the front row, was done entirely in a functional hardware description language. And one that I did at Grok involved making a compiler that was significantly written in Haskell, and functional programming was used in its verification. I'll say a bit more about that later on. This slide shows you typically what a chip layer of a TPU looks like. This is the first Grok chip. And a key thing I want to point out, it's a kind of highly regular structure. You don't have like random gates strewn everywhere. You've got replicated blocks laid out in rows and columns. For example, on the left and right of the chip, you'll see these systolic array multipliers, each which multiply 320 by 320 elements. And I think the functional programming techniques are often very valuable for being able to express these kind of replicated blocks, being able to reason about them. They have nice inductive structure. These chips are incredibly difficult to design. One of the most challenging aspects of the design of these chips is the design verification, DV as it's called in the industry. And most DV is done by testing, by simulation. So engineers write test cases and then they look at waveforms, they try and work out what's going wrong. It's a very slow, difficult process. It's not quite unusual when you're designing a chip to have more people employed on the verification of the chip than any other part, including the design of the chip. And often, this design verification phase takes way longer than any other phase. So this really makes it hard to get chips produced in schedule, and it makes it hard to innovate new designs and try new things. Because every time you try and change something, you have a complicated verification hit. The industry is really hurting from this. It's one of the biggest things which stops us from making new and novel chips faster. And I think there's an opportunity here for us to devise a different way of designing these chips. And I hope to convince you that this different way should involve functional programming and formal methods. I'm going to show you some actual wee designs done in a functional language, and I've implemented and run them on this FPGA board that I keep at my desk. So normally, I used to come with the board and I would plug it in and I would like run a wee demo. But I just found it really hard to get these through airport security because they asked me, what does this board do? And I'll proudly proclaim, what? It's an FPGA chip. It could do anything you like. Halfway through the flight, you can make a nude circuit design and download it and run it. Isn't it fantastic? I feel so proud, but airport security were not impressed by that answer. And I was already on the US no-fly list for 10 years, so now I bring you this picture instead. So another thing I'd like to highlight is the enduring power of the digital abstraction. It's been hugely successful, abstracting voltage levels on wires to zeros and ones and using Boolean logic to reason about the code. But like all abstractions, they have their limit. The digital abstraction is an abstraction and an approximation. And digital circuits only live in our heads. The world only has analog circuits in it. And so when we think of ones and zeros, really under the scene, it takes time for a signal to rise from 0 to 1 and 1 to 0, and it isn't totally flat. It's all kinds of noise and so on. So when we stretch systems to a limit, let's say we try and toggle too many transistors at the same time, even though the circuit should work at the digital domain, it starts to fail at the electrical domain. Abstractions are wonderful, but we should always understand the limits of our abstractions. So, how is hardware designed in industry? What's the current, what do most real engineers do? Well, most hardware is designed in one of two hard description languages, System Verilog and VHDL. And here's an example. VHDL is the much superior language, a very, very good type system, lots of safety features in its types to prevent you from making mistakes. It's way more sophisticated than the other language, System Verilog, which has got many problems and issues, as you're going to see in the coming slides. So, of course, the industry has standardized around System Verilog. We're designing hardware, so I guess we're thinking in some kind of breadboard or Lego kind of manner. You've got one gate, you've got another gate, and you might like to compose them together. And this is straightforward to do in most hardware description languages. Here's like a NAND gate. It's written in VHDL, my preferred language of the two. And I just instantiate an AND gate, an inverter, and I wire them up. And I used the names of the wires to connect things together. So notice that the output of the AND gate, this wire E, is the input to the inverter. And that's what forms the composition. And all you're really doing here is drawing a circuit graph. That's all that is happening. This is the same description written in the System Verilog language. Again, you see the E wire going out of the AND gate and into the inverter. And you might have some intuitive feel what the semantics of these circuits should be like. So that's quite straightforward. We have a way of assembling bigger circuits out of smaller circuits by composing them together, just thinking in terms of graphs. So we can take that description, we can give it to some tools, some Xilinx tools, and they will place and route it, and you can see that tiny blue dot on the left, that's where it ends up. This is on a Xilinx FPGA, that's the FPGA that was on that wee board, that's on my desk. And if you zoom in, you can see the two gates, the AND gate and the inverter, you can see them wired to the pins of the chip. And when you zoom in, you see the gate, the AND2 instance and the instance connected together. So we have a path from going from circuit graph representations down to an actual chip. And then But that's not actually how most hardware design is done. Yeah. The main way of specifying hardware is to specify a collection of concurrent processes, each of which contains sequential code which is algorithmically executed in a C-like manner. These concurrent blocks listen to events on wires they care about, and then they fire, potentially updating other wires, triggering other concurrent events until a fixed point has been reached. System Verilog and VHDL, they're really input scripts to event-based simulators. And here's a simple example. It's an 8-bit counter with an asynchronous reset. Whenever a clock signal rises from 0 to 1, a clock edge, this code will run, or whenever the reset pin goes from 1 to 0, it runs. And what happens, if you set a reset, you reset the counter to 0. Otherwise, you increase the count by 1, wrapping around. So this doesn't really look like a circuit. Right? It looks more like an algorithmic description. And this is very typical of how hardware is actually designed. You can then give this to a tool, like the Xilinx Vivado tool, and it will actually turn it into something that is a circuit with flip-flops in it, and gates and inverters. And then you can map that onto an FPGA. This is what that counter looks like when it's implemented on that FPGA that you saw before. And then you could run a integrated logic analyzer, zoom in, and you will see that it actually counts and does the right thing. So we have a path from algorithmic C-style descriptions as many concurrent processes which orchestrate and communicate with each other, and they get turned into a circuit graph by some tooling through a process of synthesis. And this, in general, can be quite complicated. It could take many, many hours to synthesize a circuit netlist from these algorithmic descriptions. We can also write formal properties and check them. So here's a counter again. And one super interesting thing about System Verilog and about VHDL is that they're the only mainstream languages which really have got very powerful support for formal verification as a key bolted in part of the language. So System Verilog supports LTL, linear time logic. So you can use a temporal logic to specify your intended behavior of the circuit. And here, this property here is one example. It just states that the next value of the counter is 1 more than the previous one, and you wrap around when you get to the largest value. So you can write this, and then you can write tests to check it. But more importantly, you could give this to a model checker, and it statically analyzes your code, and it tells you, yes, the LTL property you wrote is true for this circuit. And if it was not, it will give you a counter model, and it will give you a waveform trace, which will show you how from the initial state you can get to a bad state that violates that property. So that's kind of cool. We don't really, in the software world, we don't really have that. We have some examples like Daphne and things like that, but none of the mainstream languages that I know of support some kind of formal specification logic like LTL. So that's cool. So let me just give you a bit of insight into the underlying semantics of these languages, VHDL and System Verilog. So like I said, they're based on these concurrent blocks that are waiting to run. So each of these blocks is typically, they're blocked waiting to read in some signal. So when the value in some wire changes and they're listening to it, they run the code in that block. And that code is run sequentially to the end, and it can have state, it has a program counter, right? So here's some examples. Is start running, it immediately runs once to the end and then finishes. So here I am going to monitor what's happening with the values, and I'm going to kick off this chain reaction of block execution. So I'm going to set A to 3. So what does that do? Well, it wakes up the first block, A. And what does it do? Well, the A block assigns to B. It makes B equal to 2 times A. And then, then the A block goes around and it waits for another A to change. Well, now the second block is valid. It can run because B changed and it changes C. So now there are two things listening to C. The third always block and the fourth always block. So the C block will run and it changes D, and then the final block will run. But I wonder how many times it will run, because it's listening to both B and C. Will it run once or will it run twice? I mean, another way of asking this question is, what is the value of E? Is E 1 or is it 2? I mean, if you know System Verilog semantics, you know what will happen. But it is, a kind of a complicated thing. And indeed, it only runs once. When it does its listening, it's listening to both B and C concurrently. And if both B and C change, the blocker neurons ones. So that's the semantics of how your circuits operate in system Verilog. Got it? This is total madness. What does that have to do with gates and circuits and wires? I don't have an event-based simulator on my wires, on my gates. It's completely unrelated to this circuit I want to build and make. So I think this is just like some horrible crime that's been committed in history. These languages were made to simulate only hardware. That was their original design time, which is why they're designed to have a model that's efficient for simulating circuits, originally on a uniprocessor. But somehow, over time, people have warped these languages and abused them to not only simulate, but also to produce hardware, to synthesize hardware from these descriptions. And that is how most chips, including the M4 Pro and my laptop, are made. And I think it says something about human ingenuity that you could totally mispurpose something in such a terrible way and still make working chips. So what can we do? What can we do about this? Well, actually, this week, Oops/Splash, Andreas Love has a paper, and his perspective is he looks at system Verilog semantics. He studied it very closely, and he can see all kinds of problems in the system Verilog specification. In fact, the system Verilog specification is contradictory with itself. So it's got many, many issues and problems. And different simulators will do different things. If you run your circuit, if you simulate your circuit and it doesn't give you the answer you want, don't worry. Run it with a different simulator. It might work. So his solution is, let's repair system Verilog semantics by trying to modify the standard to make it sensible. And so the always blocks I showed you, they were sane, well-behaved always blocks. In his paper, Oops/Splash, he shows you much more badly behaved always blocks. So if you wanted to torture yourself trying to understand the always blocks, you can look at his paper. That is a nice picture of Andreas. There's another paper this week by Junwon Chow and colleagues, and they adopt a different perspective, which is, this is terrible. How can we possibly do anything with this? And they're particularly interested in deductive verification. So their approach is, forget about system Verilog semantics. Let's imagine what would be a good semantics for digital circuits that we can use for deductive verification, that we can use in ROC, in Agda, and Lean. Design that so from the ground up it's sensible, and then retrofit this to system Verilog semantics. And I think that's quite an interesting approach. So let's think. So where have we got? On one hand, design verification is a very difficult, challenging phase of chip design. It takes the longest part of the design flow. On another hand, system Verilog has batshit crazy semantics that are not at all well impedance matched either for design or verification. Has somebody not noticed that these two things are related? They're not independent. Maybe something should change. So what do I want? As someone who wants to design a chip, I would like to have clear, unambiguous semantics, and I want them to be able to support deductive reasoning because I want to be able to do verification and proofs about the circuits that we make. And I'd like to have like a single language which I can write specifications, I can do the implementations, and I can do the verification and proofs. A lot of the work so far in the industry has used different languages for different parts of these processes, and then they're kind of hard to correlate and put together. I also want a language that's got good support for composability. An important characteristic of chip design is that chips are big and complicated and implemented by many people all working together, and there are many challenges to do with scalability and modularity and composability, and your language should have features to support that. I would also like the ability to be able to derive an implementation from a specification, which is, I think, a more rigorous way of trying to make a correct circuit, a circuit that's correct by construction from a specification. I also would like to be able to perform algebraic transformations on these circuits. Often when I'm working with my fellow hardware engineers, we're at a whiteboard and we're drawing circuit diagrams. We've got registers, and we're moving registers from one place to another, and we're kind of reorganizing the layout. We're thinking in an algebraic inductive manner about our circuits. But this is not at all directly represented in the circuit descriptions that we write. So I want support for a more algebraic way for describing and transforming circuits, because that closes the gap between what we write at the whiteboard informally and what we type at the keyboard. I also want to be able to take total control over low-level features when I care about it, and not have to worry about them when I don't. So I would have some kind of dynamic abstractions with a wide dynamic range. And I want to have a toolbox of high-level abstractions for common idioms like finite state machines. And to top it all, I'd like to have some tooling which supports all of these activities. And I want it to be scalable, I want it to be fast, and well integrated with existing industry tools. And it would be nice to get a wee bit of help from machine learning. So I got kind of mini digression. So one thing I've always been inspired for from the 80s, many good things happened in the 80s, especially music. But this is one of the other things. So when I code, I rarely feel like a scientist or engineer. The process seems very ad hoc and informal. And I'm really inspired by the work of Richard Byrd and Lambert Meterns in the 80s on systematically deriving an efficient program from a more inefficient program that acts as a form of specification. That, to me, feels like science. So from Byrd Meterns formulation Wikipedia page, here's an example. I'm not going to go through it in detail, just want to get an impression of it. This is max segment sum. There's a specification of it at the top. It's an inefficient program, but it's kind of obvious that this is max segment sum. But it's inefficient. It's O(n) to power 3. But you can systematically apply transformations to this to get the version at the bottom, and that has got O(n) complexity, and it will be a good implementation to run on your computer. So I've always been inspired by that, because you have a fundamental connection between your implementation and your specification. Your implementation is correct by construction for this flow. There's nothing to prove. If only we could design hardware like this. And there's a diagram on the Wikipedia page which shows the various laws that are applied in each step. So I thought that was really good stuff. Maybe back then that was hard to really do for large software systems, but still a great idea. So a little bit of functional programming history. So around about 1984, after spending time with John Backus, this is inventor of Fortran, Mary was inspired by John's FP functional language. And what she did was to create a version of it for hardware design called MuFP. So it's a long time ago. And what's cool about this is she makes a direct connection between the concepts and idioms in a functional language and hardware. Composition of circuits is just directly corresponds to function composition in a functional language. Yeah. You can then put circuits in parallel, and you can apply and you can replicate circuits so that the thing to the right will be a map. And it was really nice. And then you can bend a wire back with a delay to get sequential circuits. But especially amazing was that there were algebraic properties that applied to FP descriptions, these kind of APL type things. And that let you transform circuits, change their complexity and their resource usage in a kind of systematic manner. And I thought that was really inspiring. And it reminds me a little bit of this Byrd Meterns view of the world. And totally different at the time from how everyone else was designing hardware. So then, a bit later, around about 1986, Mary Sheeran and Garrett Jones came up with a new language called Ruby. And this is like a relational hardware description language. It's some very cool, innovative features to it. So Ruby was based on the idea was you would describe circuits with relations. And these relations composed the behavior of circuits. You see here Q and R are composed by the common wire S, a bit like the system Verilog you saw earlier on. And that was written as Q semicolon R. But you also compose layout. So the R is to the right of the Q. Then you have parallel composition. The Q is below the R. And then you can do loop. And what's fascinating about these descriptors is that they also have algebraic properties. You can use them to transform your circuit to make it more efficient, to change resource usage, and to get a better layout. So I thought that was pretty cool. And being a relational hard description language, it let you do lots of cool things. You can make an inverse of a circuit. And this might not sound that useful, but there are situations where that's useful as a conceptual device. One place where that happens is when you're retiming kind of pipeline circuits, having an anti-delay is quite a useful thing to have. You probably don't want it in your final circuit, but in your intermediate calculation steps, it proves to be very useful. Super cool stuff. And then you could do these circuit transformations and optimizations very much in this bird-meeting style. This is something that's done for a systolic filter and some operations that make it more efficient. So a bit later, I thought Ruby was really cool, and it turned out that kind of thinking it could be used to solve real practical problems. So around about 1998, I joined this company called Xilinx that make these FPGA chips that I showed you. And we had these customers whose designs would not fit on the FPGA. Because in theory, when they looked up the data book, there were enough gates and wires for a circuit to go on that chip. But when you run it through the Xilinx tools, their automatic placement and routing, they just couldn't pack the circuit on the chip. And they were desperate because, multi-million-dollar customer account was about to be lost. And one thing that's important I learned is that people will not change what they're doing unless they're desperate and they have no other path and they have exhausted every other path they could possibly take. So they asked me, Sam, is there anything you can do about this with your weird Haskell stuff? So I kind of looked at their circuits and I thought, this is a filter. It's this block which is replicated left to right, and that if you laid it out in a row, you minimize the wire lengths and you efficiently pack things. And this thing should be done like a triangle because of the pipelining and so on. So I made a version of Ruby in Haskell. I called it Elava. And this composed behavior and layout. And then when you write circuit descriptions, it generates VHDL at a time, but they also compute the XY coordinate of every gate. And then the customer designs worked, and they were happy. And then I got to do lots more Haskell, lots more Lava. So behind this is these Lava descriptions are these individual gates where we compose behavior and layout. And each gate is in its own coordinate system and its grid. And when you compose them, the Lava will know the width and height of each cell. And if you're doing like a serial left-right composition, it will shift something along by the appropriate amount, and you get a result back in a new layout grid. Very much inspired by this work done on Escher's fish by Peter Henderson at Oxford. And let me just tell you a little bit about how all this works, because it's incredibly simple. There's nothing sophisticated or clever about it, which is what I think is good about this. So at the root of this, there's a type class for Lava, and it's parameterized in two things. It's parameterized on bit, which represents the values that flow over the wires, and it's parameterized on M, some monad. And then you have like gates like an AND gate, and you have delay. And then the reason for this is we want to have multiple interpretations for circuits. We want to be able to simulate them, generate lists, draw them, compute things about testability. If you want to simulate these circuits, well, we don't need the monad for anything. It doesn't buy us anything. So we can instantiate the class of the identity monad. And we can model the value in wires as just being lists, booleans. And then you get the obvious descripts. Implementations for inverter just maps the Haskell not and to. And delay just takes infinite lists and adds an initial value false on top of it. And then you can directly in your REPL in Haskell simulate these circuits, which I think is very, very cool. I didn't have to write a simulation framework or an event-based simulator or whatever. You run these descriptions directly. And this is how the previous NAND gate, this is how you would do it. And when you run it, it gives correct implementation. And then there's another instantiation you can make. This time, I'm going to use a state monad to help build up the circuit graph and keep track of the nodes and edges. And then when you run this, you get some system Verilog or VHDL from the output. And then the other cool things are you can model loops just as regular top-level Haskell functions because we have monad fixed. So we just bend the output wire and put it in the input. And notice at the bottom, the C occurs on the left and the right-hand side of the monadic bind. But that's not a problem. We have lazy evaluation. and we have monad fix. As long as you only consume a finite amount of the output, this thing works, and you can sort of simulate sequential circuits. You just run these things. There's no interpreter or anything else over it, and I think that's such a beautiful, that's such a beautiful thing. The real Lava type class has got other things in it to let you do efficient implementation for Xilinx FPGAs and layout combinators. So let's see an example of this. For this example, I'm going to make use of Leonard, thank you, orthotope array for letting me have vectors whose sizes I can track at the type level. So it gives me like dependently typed vectors in Haskell. And I'm going to do one of my favorite circuits, batches by atomic sorter, which you're going to see in several forms in this presentation. And what this is so this is a sorter, which is a network sorter. This one takes 1, 2, 3, 4, 5, 6, 8 values, and after it and each node is a 2 sorter. It will sort 2 values, and then if you push left to right to its network, at the output you'll have a sorted version of the inputs. And it's built with a butterfly of a merger, which is what's on the right, and 2 smaller sorters. So you can sort of see that structure there. And we can just keep inductively applying this process until we get to the base case, and you get the picture that you see on the previous page. So the 2 sorter, the base element, we can write in our Lava hardware description language using par and swap, and we'll use a subtractor and to compare the 2 values, and then we'll have some multiplexers so you can select the bigger or the smaller. And when you lay it out in the FPGA, you get this nice layout for the 2 sorter. And the other thing we need are a bunch of divide and conquer combinators, which take a big problem and break it down into 2 sub-problems, solve those, and compose a result. And one nice example of that is something called interleave. What that does is it takes some high order parameter R, some circuit, and it creates 2 instances of it, one laid above vertically the other. And it takes the input and sends the even wires to the bottom R, the odd wires to the top R. They do their stuff. And then at the output, you undo the even-odd split. And you define it by unriffling to R. Riffle 2 is another high-order combinator, which does the vertical stacking. So we're going to use this a few times in this presentation. And then there's another one called evens, which takes some circuit that takes 2 inputs and 2 outputs. Oh yeah, one thing I'd like to emphasize about interleave is that you can only apply it to even-sized inputs, and that's enforced by at the type level, at the dependent type features that we get from Leonard's library. So evens takes a circuit that takes 2 inputs and 2 outputs, and it just replicates it across an input vector. But the input vector has to be of an even length for this to work, and that is enforced at the type level. So then, how do you make a butterfly? Well, we can do a nice dependently typed butterfly, and we could create one instance of it for degree 1, and that would just give us a 2 sorter. That's what sorter takes 2 inputs. And for a larger butterfly, we interleave 2 smaller butterflies and then apply evens at the end. And this will give us batches bitonic merger. And when you run it, it produces a system Verilog where the XY coordinate of every gate has been automatically computed for you, even though you didn't have a single XY coordinate in what you wrote. And then when you give it to tools to place and route, this is, for 8 input sorter, this is the picture you get. And I think there the butterfly pattern is clearly evident and looks similar to the original picture that I saw, which I think is quite beautiful and nice from these simple algebraic descriptions with beside, below, par, etc. You've composed behavior. This thing will sort numbers when you put them in, and you get a nice compact implementation of the sorter on the FPGA. This is a bigger sorter of 64 inputs, and this is what it looks like on the FPGA. It looks like a solid rectangular block, and if you sort of zoomed in, you'd see the nice wiring pattern. And this is one that's 128, and if you zoom in, you get a nice wiring pattern. So most FPGA circuits don't look like that. You can't look at the layout, and because the place and route system will just pick some place where it thinks is the best place to put them. So this is the same sorter, but with all the layout information erased, and you can see, it doesn't have the nice structure that you saw before. And if you put the wiring pattern on top of it, where is your butterfly? Butterfly's been squished. It involved a bit of Haskell extensions to make that work. And thank you for the plugins, Christian. And I got some help from some people for writing this code, because I wasn't clever enough to write it myself. So thank you, Dominic, and thank you, Leonard. So you could, I have a confession. You could have written interleave in C++. And C++ will, at the type level, will statically at compile time check to make sure that you give it an even-sized array. And if you don't, it will give you an error message. So you can write functional programs really in any language. So what does it mean to be a functional programmer? Why are we all here? What is it that binds us together? Well, I think being a functional programmer is more than just what I type into VS Code. To me, being a functional programmer speaks about shared values, about how we write software, common idioms for programming, the design of libraries, and a special network of kind of like-minded functional programmers that we hang out with. So I am a functional programmer, not because of the company that I work for. I am a functional programmer because of the company I keep. So thank you all for keeping me company this morning. So now let's get back to chips and try to verify chips. So at my previous company, Grok, one of the tasks I had to do was to verify a special type of network switch called a BNS network. So what a BNS network will do is it will take some n bits in, 32 in this case, and then with some control bits, it will permute the output. The output will be a permutation of the input. Like, for example, you could reverse. The output could be a bit reverse of the input. And if you go to the Wikipedia page on closed networks at the end, you see a nice picture of an 8-input BNS network. So my job was to formally verify the implementation that the engineers had done of this in System Verilog, which is gnarly and complicated. So I thought, how would I do this? Well, I have all the tools I need, because I know how to express a BNS network. It's a butterfly network, and so I could do its implementation as even swap, and an interleave of two smaller BNS with even swap at the output. But that's not what the engineers wrote at my company. So how did I verify their System Verilog code? Well, I had this multiple interpretations for these descriptions, and one of the interpretations I have is I can make a circuit draw itself to generate some SVG. So I wrote this description, I instantiated it for size 32, and I drew the diagram above. This diagram is the formal specification, right? The goal, it is the source of truth. So you look at that diagram, you compare it to a Wikipedia page. As long as you trust the person who did the diagram on the Wikipedia page who knows what we're talking about, this is the formal spec. Now the goal is, does this picture correspond to what the engineers wrote, right, in the System Verilog? Well, how can we do this? Well, another interpretation of this is to make it generate some System Verilog. So it can actually generate some System Verilog code. And that System Verilog code is just a textual representation of this picture. It's isomorphic. It's the same thing. So now I've got two System Verilog bits of code in my hand. One is basically that picture, but in code. And the other is the gnarly, complicated System Verilog that the engineers wrote. So that with these two programs, I can run a standard industry tool called a logical equivalence checker. It's a formal verification tool. And it takes two circuits, and it can tell you if they're the same or not. And the system, I ran that tool, and the proof went through, and it verified that the engineers' implementation matched the System Verilog code that I generated. The System Verilog code was isomorphic to the picture, so I had done the verification. So that was kind of like cute. It's not often you get a picture that acts as a specification, and then you can make a proof go through. All you have to do is believe whoever made this picture on the Wikipedia page knew what they were talking about, and you had to trust them. But let's look at that diagram and all the colors and wires in there. It looks kind of familiar. I wonder who actually drew that diagram. Maybe there's some circularity here. So I showed you how to use these wonderful combinators to do circuit implementation and layout. You can also use them to generate code to run machine learning compilers. And one of the operations that occurs commonly at the end of most machine learning inference pipelines is something called top K. It picks the top n features that are most likely for what you're looking for. So let's see if we can build this using the same combinators. So we need a 2 sortrix, and we can write a 2 sorter again using the same combinators, except this time, this is code that's going to run on a machine learning chip. So when you compile it, you get some MLIR code, which is a machine learning framework for compiling machine learning programs. And it's expressed in terms of reduce min and reduce max operations over tensors. And then you can create a bigger version of this, the butterfly, and when you generate code for that, you get many, many instances of these 2 sorter bits of code all stitched together in the butterfly pattern in this MLIR. And then when you run it on the chip, the thing is now doing sorting, all the values going between the memory and the VXM. So that's kind of cool. The same source code for these combinators gets used in one way to make the chip, and the other way to produce programs that run on the chip that it was used to make. I think that's a little bit mind-bending. I think it speaks to the power of these combinators, these high-level, higher-order abstractions. They've just got so much use and utility and reuse. The pictures of the butterflies that you saw here, you'll see them again in a paper tomorrow called Fools Seldom Differ. It will be presented by Craig Roy, but it clearly has Conrad Breid's fingerprints all over the title. This is the picture that you'll see that, and you'll get the full treatment tomorrow. So we'll have another digression. What was I going to say about Steve? So let's talk about Steve Hand, and he is a well-known systems researcher. And he teases me rotten. He says, Satana, for programming in these functional languages where you know the value of everything and the cost of nothing. And you just can't understand why I love Haskell and all these other functional programming languages. But I think it's because I've done all this low-level work that I love functional programming. I love Haskell because these languages give me the tools I need and lets me build up the high-level abstractions I need so I can do these low-level optimizations and remain safe and avoid errors and mistakes because I have the guardrails of the type system to keep me on track. So what I would say is. And I think maybe what makes it different from Steve is I love programming languages not for what they do. I love programming languages for what they are. And I think maybe that's what makes me a PL person. So let me tell you about another functional language which I have nothing to do with the design, but I think it's like the best example. I think it's the best hardware description language we have in the world. At the moment, right? So the most fit-for-purpose thing that I think has ever been devised. So with languages like Lava and there's many other languages that are similar, they're fine for doing structural design where you snap circuits together and design kind of in the small. But as soon as systems get large with many modules, I think things start to fall apart. And then you don't really have any help with control logic, finite state machines, things to concurrency, race conditions. There's just so much more that you need to worry and take care of. And the BlueSpec language, I think it is the best answer to all of these things. And I was trying to work out roughly when it came around. I think maybe around about 2020. Here you see a picture of Arvind, who's one of the main people behind BlueSpec. Many other people were involved as well. And so lots of good things with BlueSpec. So one is BlueSpec borrowed heavily from Haskell. So it has all the loveliness of types in Haskell. You have it in BlueSpec, and at that time even more because you had support for dependent types. You had 2 surface languages, one which looked like Haskell, which I really like, and one which is made to look a bit more like System Verilog to try and convince and trick real hardware engineers to use it. And at its heart, semantics is based on guarded atomic actions, which is really a super powerful feature to let you do scalable, race-free, correct hardware description. So I can't do justice to all of BlueSpec, so I'm just going to give you a wisp of a feeling of what it's like. So here's again a running example, a counter. And notice in BlueSpec, you have an interface to the counter, and it's got methods, which might remind you of methods that you have from other languages. And in the implementation, you have some state. Here, the state is the value. So that you see the register there is created with an initial value 0. And what can you do? You can read from a register, you can load a register, and you can increment a register. And what's different from System Verilog is that you can break up, you have different bits of code which operate on a shared state, write them in different places, focus on just what that bit of code does, and then BlueSpec will stitch things together itself and schedule them in some way that's totally safe, that avoids race conditions, etc. If you had to write that in System Verilog, you are the scheduler. You have to write all that code, and it all gets written in one place in one block with no modularity. So that's already a huge advantage. So what's the semantics that's here? Well, there's a lot of questions you might have about how that code runs. Can read and increment be invoked on the same clock cycle, or do they conflict? And if so, does read return the pre-increment or a post-increment value? Can load and increment be invoked in the same clock? If so, is the final value in the counter the load value itself, or the load value incremented? And can read and load be invoked in the same clock cycle? If so, is the read value the preload value or the post-load value? These are all things that you should probably worry about this code. All these ordering questions are made precise by the serialization of atomic transactions, which fixes ordering on the methods. Without more information, the compiler will choose an ordering that's guaranteed to be functionally correct, so no race conditions, and it will inform the user of the order chosen. Or the BlueSpec user, through annotations, can specify any desired static ordering and conflict semantics. So, of course, you could do complicated things as well. And the butterfly that you saw before, you can very nicely write that in BlueSpec as well. And this is some of the code of, this is a complete code of how you would write the butterfly. And at the heart of it, you can see the base case and then the recursive case where you make a big butterfly out of smaller butterflies. And for me, one of the key benefits of BlueSpec is it lets me reason in a modular manner. In the world of software, we're used to getting A to work and B to work, and we kind of hope that the composition works. But in the world of hardware, that never happens. We have all these protocols and transactions over the bus. But BlueSpec gives you back modular composability in a way that we kind of have in the software world, but we never really had it in the hardware world until BlueSpec. So at Google, the first TPU chip that I showed you, Leonard and I worked on it. We wrote it entirely in BlueSpec. I think it was a huge success, and the code looked wonderful, and the chip came back and worked first time. Mike Gunter was the person who led that project, and he's now still doing machine learning chips. He's got a startup now called MatX, and they're making some they're in stealth mode, they're making some fancy, another machine learning chip, and they're still doing it in BlueSpec. You might think Jane Street is a company that makes nice t-shirts. And the t-shirts are very, very nice. But they also make a hard description language, a functional hard description language. So there is a language called HardCaml. Of course, it's no camel. This is what a running example counter looks like, and it generates the following system Verilog. Now, going back to Lava, that was a DSL. It was a library in Haskell, and as a user of DSL, you know all the problems of DSLs. But it would be nice if you could directly write some Haskell and have a compiler that takes the Haskell, parses it, and then turns it to a gate. Well, that's exactly what the Clash system does. And Christian and co have been doing this for a while. Absolutely fantastic work. This is an example of a binary to gray converter and a gray to binary converter and how you would write it in Haskell. And the Clash system will take this and it will turn it into gates. Super cool. But it gets cooler. One thing I've always worried about functional programs in Haskell is I can never prove anything about them in a systematic kind of manner within the language. But we have liquid Haskell now. With liquid Haskell, we can prove things about a program. So why not connect Clash and liquid Haskell together? So you can write directly in Haskell, produce circuits, and then use liquid Haskell to do proofs. And the Clash people are doing exactly this. It's early stage work, this is a theorem about which says if you do binary to gray and gray to binary, it should be an identity function. You can write that in liquid Haskell and Haskell, and you could give a proof. It should remind you of Bird-Meertens or whatever, and QED, it kind of works. So this is like new work that's just starting, but I think it's kind of an interesting, promising approach. I'm surprised by how far we can really go. Then I would say at the frontier of new hardware description languages is a language called Filament, done by Ratchet Ningham, who's now at MIT. And the cool thing about Filament and the following languages is that in the types, you can say something about the temporal properties about circuits, which then lets you build up an IP catalog of circuits and compose them together in an efficient way. I don't have time to do justice to how it all works, but if you're into hard description languages, check out Ratchet's work. A quick digression for the functional programming PhD students in the audience. When you're doing a PhD and you're working on some proof or some niche, narrow thing, it's easy to get despondent and wonder, why am I doing this? How is this connected to the real world? This seems so academic and obscure. Well, as someone who came from the PL world, did a PL PhD, one thing that's clear to me is that the PL PhD, it gave me a huge toolkit of conceptual mechanisms for solving problems, and being able to apply the techniques that I learned as a PL person to a wide variety of areas, to not just programming languages and compilers, but in systems and Kubernetes and all kinds of things like that. So I would say, even when you're in the depths of a very narrow thing in your PhD, remember you're getting training, which is making you a more general problem solver, and that will come evident over time, and will have a range of applications that you don't yet realize. Another way we try to do proof, right, for these in a language for circuits is to just use a proper theorem prover. And Google had this project called Silver Oak. It's not on GitHub, where we used Rock, and we made a DSL in Rock, and we implemented circuits, proved properties about them, and verified them. And I had very good help from people that knew how to write Rock proofs very well. And we do the same type class tricks in Rock that we did in Haskell. And we took an AES block, and we did a spec implementation and proof. And the proofs were they were quite hard to write. So how can we make proofs easier to write? Well, let me just give you. I'm going to show you something, which is going to get me in trouble. Does this come up in this? Okay. So what I want is, at Grok, I started to describe circuits in Agda. And I wanted some help to do the proofs. So what you see here is VS Code with an Agda lemma in it. It's any all lemma, which is De Morgan's law listed to list level, from Phil Wadler's Agda book, is at hard exercise. And I wrote a wee program which connects to an LLM, and at the bottom you see the LLM trying to come up with a proof. So I just give the lemma in Agda to Opus 4.1, and then after a few iterations, Opus finds a proof, the compilation is successful, and then I double check it in my ID, and it's worked. I thought, oh, that's quite cool. Maybe we can actually get machine learning to help us actually do proofs for our circuits. So let me return to my presentation. So that would be cool, because if you could get a theorem prover to help do that, you could try and do these circuit proofs, and then when you get to a certain level, you can shoot the aliens down by just dispatching to an LLM how to do the proofs. And I'm really inspired by the companies that have won these at the Maths International Olympiads gold medal. DeepMind got a gold medal this year for the International Maths Olympiad. So did OpenAI, and so did this tiny small startup of about 18 people in Palo Alto called Harmonic. So, and their approach involves using Lean. They took the problems, they expressed them in Lean, and their engine, their machine learning model, consumes Lean and a Lean lemma and tries to give you back a proof. Absolutely amazing stuff. It's almost abstract. And what's cool about this is that you can check the result of the LLM to know if it's lying to you, if it's hallucinating. Because you can take the proof it gives you, you can give it to Lean, and Lean will tell you whether it's correct or not. I think that's like an amazing property. And so it would be cool if we could use this to make hardware better. And I think what we should do is take, in Lean, build up a library for hardware design, but we should not base it on the batshit crazy semantics of System Verilog. We should not base it on Mealy-Moore machines, the machine-coded sequential circuits, or Kripke structures that are used for border checking. We should base it on a sensible semantics for circuit design, which has been proven to work. So I think we should take BlueSpec's semantics and code them up as a library in Lean and use that as a basis of how to design hardware, verify hardware, do proofs, and do implementations. So, guess what's happened? I'm done with these megacorps. I'm not working for them anymore. Next month, I'm going to join Harmonic to do exactly that. So stay tuned. Functional programming and hardware design has started a new chapter. Thank you for your attention.
Thanks, Adna. That was such a great talk. Everybody's stunned and has nothing to say. So that was an amazing talk. I really liked that go over the history. But of course, it was also a very depressing talk because you explained how back in the 1980s, Mary and Kuhn and you and all these other people already knew how to do all this. And since all that time, people are still doing it the wrong way. So you talked a lot about the technical things. I wonder if you would say a little bit about the people side of it. You did touch on this, yeah. But I wondered, what do you think has been the most successful human engineering of this to get people to use it, and B, how do all the young people in the room carry that forward?
So I'll answer this in reverse. I think a really great example of doing things differently for verification is the ACL2 system produced at University of Texas, which has been used to do a form of verification of large chunks of x86 style processors. It's not used to design hardware, but it's used to verify hardware, and that's all based on functional programming. Why is it like this? Well, hardware engineers fear abstraction. Abstraction is not their friend, it's their enemy. So when I worked at last company, Grok, there was a situation where somebody had used a struct as a type on the interface of a module, because these signals were grouped together logically, so you should have a struct. And then in code review, that got rejected, because lots of hardware engineers hate a struct. They don't know what that means. How are the wires laid out? Will some inefficiency be introduced? And the person who wrote that code had to delete the struct and replace it with the individual wires that made it up. Right, that was this year, right? This was not in the past. So engineers fear abstraction because they think it's going to make their circuit inefficient, it's going to add extra gates, it's going to add extra logic. And that's just a cultural, social thing. Engineers are conservative. If you make a mistake and you tape out your mask set, you've lost millions of dollars, you've lost 6 months, and you've lost your competitive advantage, and that chip may no longer be viable. So there's an inherent conservative, these people are inherently conservative. However, I think there's hope, because I think the verification pain has got to such a level that they have to do something different. And that's why I highlighted that about when I worked at Xilinx on Lava. It's only when people are so desperate and they've tried every other approach and it hasn't worked that they would try something different. I think we're there with chip verification. People are so desperate that we developed a different flow that could give high assurance, proved correct, formally verified, proof by induction, proofs of big complicated circuits. I think people would buy into it because there is no alternative.
So you mentioned ACL2. I'll just tell you an anecdote that I was told by Jay Moore, one of the developers of ACL and ACL2. He just put up this little graph of what they could do. It started very tiny, right? But it went up by 1.5 every year, Moore's law. And so by the end of it, right, they were verifying entire computers. And all you need to do, I think that if you look at the progress of Haskell, it's been the same thing. You just do something good, teach your students, let them out in the world, and wait 30 years.
Yeah. Thank you for your question, and thank you for the NAL LMFO.
Hello. A more technical question. you talked about having a very simple system to assign the XY coordinates, and that gives you a very structured representation if your input was very structured. How does it, you might not be able to fit this into your space that you have. How does it interact with like optimization, where you might want to actually squash stuff into?
We just have layer combinators which will, if something's too wide, then you have a combinator which will break it at some articulation point and bend it around, or snake it, or whatever. So you have a toolkit of things which lay things out as you want them in any way. Mm-hmm. I didn't have time, but I was going to do Escher's fish diagram, if you might be familiar with, and I was going to lay it out in a chip to show you the flexibility of layer combinators. You could definitely do that.
Mm-hmm. Thanks.
Hi, but there's a tension there, right? Because when I'm thinking of a circuit, if I want to use all the high-level abstractions that functional programming gives me, like in some of the examples you gave, I might write down something that if I normalize that fully, there's no 2D structure to it at all. It's not even possible to lay it out. So there's a tension between wanting to control the layout and wanting to describe circuits at a level where I can't really see as a human that it's going to...
So in a far too small font in the real-time class, you had a bunch of combinators have got no layout associated with them, so they just get code from that is automatically placed and routed by the system. And you have other combinators that do layout. So if you use Kleisli arrow, I didn't define Kleisli arrow, it comes from control.monad, and you compose that, no layout is computed. You have to use my special, greater than minus greater than, and that. So you get to choose what you want to lay out.
You were suggesting that BlueSpec is like the state-of-the-art specification language here, but you showed these examples in Haskell where you're making use of dependent types. Does BlueSpec support that functionality as well? Oh, so you can do all the static guarantees there as well.
It had those features, well, thank you, Leonard, long before we have them in the form we have them in Haskell, yeah.
Oh, great, thanks.
So Satnam, thank you. But you're kind of presenting it as if hardware design is now a solved problem, right? Functional programming has conquered the world. But actually, it's still pretty hard. It's still pretty hard to build really big chips that work, and it's hard enough just to get them to give the right answer, let alone be laid out nicely and with the right kind of delays and power consumption, all that kind of thing. So where's the next frontier, and is functional programming going to help with that?
Well, I mean, so. I think some of the layout stuff, and that's kind of cute, but most people don't really do layout unless it's for some super critical thing. Though I did work on my last company, I did actually work on something that needed that level of layout control. I think the most important and challenging problem in hardware design is verification. It's what's stopping us from innovating new chips, adding new features, trying out more powerful optimizations, because we don't have the verification to keep us on track. And every time we need to re-verify, it takes too long. So people focus too much on trying to design languages to express what you want to compute. Well, I think we need to think about what we want to specify and we want to implement. Specify, because I think the role of machine learning is going to become more and more important for hardware design as we use LLMs to generate circuits and properties and help with proofs. And for verification, I think we need to do something different from the kind of the model checking that you saw before for the counter. It uses the model checker, but these model checkers will run out of capacity when there's too many state bits in your circuit, and suddenly you've fallen off a cliff, you can't verify anymore. So I really think we need to look at deductive reasoning techniques and make those viable. So that's what I think the next step, right? Take something, a language that's got successful kind of scalable semantics that have been tested and shown to be working, like BlueSpec, encode them in something like Lean and produce like a DSL for hardware, which we use for design, implementation, and specification. That'll be a new thing in the world that we don't have today. It isn't solved, but I think it's a path to a better world.
Satnam, we wrote a fun paper about 15 years ago about reconfigurable FPGAs.
I remember that.
And I was just wondering, what happened to the reconfigurable part? Because it seems that the use of functional programming to quickly specialize and have a really dynamic world might be a thing, but it seems to have disappeared now.
Yeah, I mean, I think, again, if you say to an engineer, You produce this beautiful circuit that you've spent 5 months verifying. Oh, by the way, at runtime, I'm just going to totally mess with the gates and totally rewire it as it runs. I mean, this is not a Python program. This is like a circuit. You can't be just like rearranging it as you run. So people are kind of scared of that. You really need, I think that's a great use of form of verification to prove that you only reconfigure in a sensible kind of manner. And then, in a previous life where I was academic, we actually had research projects, people like Tom Mellon and so on. We actually did proofs that circuits would reconfigure in a nice manner. But how many people in the world can do those proofs and believe in them? So I think dynamic reconfiguration was hard to sell because it was hard to verify.
Hi, Satnam.
Hi.
Hi. Max New, University of Michigan.
Hi, Max.
I had a question about your example using monad fix. So you were expressing the recursion in the circuit using value level recursion in Haskell. So I could see how that would work for a simulator, but you're also able to get
imposed by development cycle costs imposed by place and route. That seems to be the biggest bottleneck in people iterating more quickly on getting, say, performance feedback and lots of other things. I know it's different than what you're talking about, but maybe you have some thoughts.
Yeah, I mean, place and route for FPGAs can take hours. It can take more than a day, right, for a chip design. But that's not something I really kind of worry about. I think simulation for verification is much harder. Those runs can be longer than the kind of place and route runs. So that's the friction for people, right? They've got an idea, a test or property they want to check, and it takes, it could take a day to run the simulation, or your model checker runs for ages and then it gives up because it runs out of capacity. So I think the iteration that's the most painful is the verification iteration, not the implementation one.
Hi, Satnam. I'm Dan from the University of Southern Denmark. I was just concerned that your Haskell programs were too beautiful. And I was thinking about how, like, Robert Frost can say in 10 lines what I could not say in 100,000 words. So I wonder if that is an element at play that, functional programmers, I mean, you can put a lot of thought and express something really beautifully in a way that you can easily verify, but that most engineers might not be able to really wrap their hands around. Is that an issue in this space or not at all?
I love the programs for what they do. I love the programs for what they are. And I think they're beautiful descriptions, and I like them anyway. I don't care what the engineers think.
Okay, I'm afraid we'll have to stop questions there. Let's thank Satnam for a fascinating talk.
Thank you very much.
Chair should recruit the people. Hello, hello. The session starts in 1 second. No, minus 10 seconds.
I think a lot of people are still eating.
Yeah. I need to go out.
Because the previous talk, I think, went a bit over.
Okay, hello everyone. This is the first session on dependent types. Please take a seat and let me announce our first speaker, who is Thomas Lamillon, and he will talk about two functoriality of initial semantics for binders and substitutions.
Okay.
Hi, so today I'm going to talk about some work we did with Benedict and Ambroise Lafont. So Ambroise not there today, but Benedict is here somewhere if you want to bother him with question, over there at the back. So basically, our work asks the question, how do we relate models of different implementation? And at the end of the day, everything can be summed up into one slogan, which is two-functoriality. So in this talk, I'm going to try to explain you the problem and why this slogan actually is a solution. Importantly, you need a very basic concept of category theory, but you don't really need to know definition, two categories. The point of this talk is really to convey and explain the principle that lies behind using two-functoriality. So first, let's recap a bit the concept of initial semantics, because I imagine that not everyone is aware of it or very familiar with it. That displays correctly on my computer. Look at this. Is there something to do about it? Well, we'll do it this way then. So the most well-known example of initial semantics is how do you model your inductive types? if you want to modelize inductive types, you give yourself a notion of syntax, which is just like a functor of a base category. And then an inductive type is modeled by an F algebra. You have a base object that represents your terms, and then you have a constructor which goes from f of x to x. And then your morphisms are just like functions that preserve constructors. The most simple example you can think of are lists, and it's just you're going to take an inductive type on the base category set, and your functor is going to be 1 for the constructor nil, because he has no argument. And then the constructor const has 2 arguments, a and an element of list, which is represented by x. So you're going to get an argument a times x. So then for your list, you're just going to model it by F algebra for this functor. And every such model is going to have the structure and the constructors of list. So you're going to tell me that is great. That is great, you've modeled inductive types, their constructors and their structure. But how do you actually capture recursion principles? Because when you try to do proof about a language, that's what you need the most. That's where comes the initial part in initial semantic, because you characterize your inductive types as initial models. So for inductive types, you're going to be initial algebra. It may sound a bit abstract, but it actually unfolds quite easily, because a model is initial if it can be eliminated into any other model. And so how do you get recursion out of that? Well, basically, if you look what it means to build a model, it's exactly recursion. If I can build a model, then I have a function in this model. If you unfold this definition to list, well, you actually get the fold function when you're doing programming, or you get recursion principle if you're doing proof assistant. That is just going to tell you, if I have a base element, and for every a and not a base element, I can build an element, then I get a function from list to y, list of a to y, and this computes how I would expect. The base element is mapped on the base element, and the constructor sequence is going to be mapped recursively const to sequence. So this concept is very broad and very general, and you find it for a bunch of concepts, or as it is to model equation, reduction rules. It always comes in the same scheme, which is you define a notion of signatures to be able to specify your object. On top of that, you define a notion of models that try to capture some properties, and then you try to prove an initiality theorem result, which is basically supposing reasonable stuff I can actually prove in real life, then there's an initial model. And then you get to initiality, you're going to get an initial model. And what's important is that your model is really initial as a model with all of its structures. So if your model captures like reduction rules or semantic properties or binders, you're going to get a recursion. Your principle is going to be substitution safe, or it's going to be preserving your equalities or your reduction rules. And so that's really the power of initial semantics. So now that we've discussed a bit like what's initial semantic, what do we care about in this talk? In this talk, we really focus on like a tradition that has been started in 99, rather a trend that was starting in 99, that tries to model languages with non-dependent binders, like OCaml or stuff like that, but not ROC or ACDA, and try to capture them with their substitution structure. So you really want to capture binders. This tradition is particularly interesting because there's been many papers on the subject to extend it with equation, reduction rules, or strategies. In this talk, we are not focusing on them, but we do hope that our work can scale to them relatively fine. The very particular trend we focus on was started in 99 by Fiore, Plotin, and Turi, and continued by many people like Mattes, Arends, Hirschowitz, or Saville, and many people have been working on that. There's many papers, and I'm just citing a very few number of them. There's other works like nominal syntax to capture binders, but we're not really focusing on that here. In all those papers, you're going to get a bunch of different variations. And in the previous work, we like really worked on getting a common language for these different models. And using this work in this talk, we're going to be fully abstract. We're just going to say, suppose you have a base category that is monodal categories in our case. We have a notion of signature, a category of signatures according to the scheme I've shown before. And then for any signature specifying an object, like list, you're going to get a category of models that's going to capture your binders and your substitution. So what is the problem? The problem is that as soon as you try to define a workshop like this, the first thing you do is choose a base category. For set, we have chosen to interpret for list, we have chosen to interpret it into set. But we could have chosen like DCPOs, we could have chosen a bunch of different base categories that will carry different meaning, depending on what you want to do. In our case, our base category mostly captures the notion of context and binders we're trying to use. So we could use BN to set, doesn't really matter what it is. And in this case, we will get a Dobrain implementation. We could use a functor category like F to set or set. In this case, we would get a whale scope syntax that would be intrinsically defined. And well, the question is, how do the models relate? Because by choosing different base category, different instantiation of the framework, you can actually get different implementation. What is actually kind of interesting is that we actually have relations on these base categories. Those different base categories we've chosen are not unrelated. So we are actually implementing the same language, and it makes sense. If you want to model binders, you do need a little bit of structures. So if those base categories are related, are the model related? And also, since we've seen that our implementation is the initial object, are the initial objects related? Are they the same? Are the implementation the same or at least equivalent? This problem can be seen in a different way as soon as you try to consider typed languages. Because if you want to model something as simple as the simply typed in the calculus, well, you need a set of base types. And then your base types are going to end up being hard-coded in your base category. See, for instance, for the simply typed in the calculus, if your type system is U, your base category is going to be set power U to set power U. So basically, it's like discrete functor from U to set and discrete functor from U to set that basically as a context. And what's important is that U and V appear in the base category, it's fixed. So if you would like to translate a simply typed in the calculus to another one, for instance, if you want to translate, I don't know, PCF and you want to erase types to the untyped in the calculus, how do you actually do that? If you want to use initiality in a too naive way, you will get stuck because initiality requires two models on the same base category. So here, as soon as you try to use this framework in the type case, basically you get stuck because your recursion principle is just not strong enough. So our problem to solve is basically this one. How do you relate languages that are the same languages but defined over different base categories? And for that, we have a simple solution that basically packages all, is to say that your models are two functorial. And you don't really need to know that much more out of that to be able to use it. So where do two categories pop up? The thing is that we have relation on the base categories. So monoidal co-reflection, it's actually quite important because a co-reflection is an adjunction that preserves initial object. So we know that the initial object in each side is the same for the base category. So we can hope that the initial object for the models, that is the implementations, are the same. Similarly, as soon as you have a function that translates a type system, so U to V, automatically you get a monoidal functor on your base categories. The thing is that those relations are actually generic concept. If you attend the basic intro class to category theory, you're going to see this concept in the category of categories. You're going to see this concept in the categories of monoidal categories. But importantly, all of these are two categorical concepts that can be defined in any two categories. So if you want to work and reason about this kind of relation and categories built on top of that, it's actually very natural to step up to two categories. And two categories actually appears very naturally because basically we had a base category and we had a signature over it. And this can just be assembled by taking, well, a pair of a base category and a signature over it. And then you're going to get some two categorical structures that appear quite naturally, though it's not trivial. And then, importantly, you just get a model, a model functor that, given any base category and signature over it, builds you the category of models. And so it's nice because if we have adjunction or equivalencies in modsig here, we'll be able to lift them automatically to cat. So this being said, let's see how it solves the problem, because we don't really need to know more than that. If you look at the untyped case, well, you can very easily define a sub-notion of categories that are just the categories with enough structure to interpret your untyped languages like the untyped lambda calculus. So basically, you can just restrict your functor to get rid of the elements in modsig that are basically too general to actually, well, interpret untyped languages. And then as soon as you've done that, you have your scheme. If you have a co-reflection f set to set set in the monoidal categories, you just have to show it's in particular co-reflection in your categories with enough stuff to actually interpret your untyped languages. And then automatically you can lift it, and you're going to get that for any binding signature, you get a co-reflection for the models. So for instance, this tells you that for the untyped lambda calculus, you have an adjunction, a co-reflection, between your models on F set and your models on set set. And what's important here is that because a co-reflection preserves initial object, here in both categories, the initial object, that is the implementation, are going to be equivalent and the same. You can implement one with the other, and you can switch from one to the other relatively easily. The simply typed lambda calculus issue is a little bit more complicated, but basically the way it works is that you want to relate signatures of the different type systems. You want a more generic recursion principle. And if you want to do that, you need, in a way or another, to parameterize your notion of signature by the type system. And you can do this relatively easily for simply typed signatures. You can just say, okay, let's take a pair of a type system and a signature over it. Because, of course, the signature of the simply typed lambda calculus is not going to be the same as the PCF language, because in simply typed lambda calculus, you don't necessarily have Booleans. You don't necessarily have natural numbers, which you can have in PCF, in which case you will want different signatures for them. Then you can just define a notion of morphism that is just going to be a translation of the type system that preserves the constructors. So what it means is literally, if in my signature, where I'm expecting a Boolean, I translate it to a natural number, then I must map it to a constructor that does take a natural number. You're just compatible up to retyping. But most importantly is that this forms a category as basically everything you consider as soon as it's a little bit well behaved. And you're going to be able to build a functor from your notion of signatures to the model. Something that's important is that here you use only the one functoriality. We won't use the two functoriality. So you're going to tell me, and rightfully, how does that get us closer to have a generalized recursion principle? Well, if you just look at it like that, you're a bit closer, because already you're parameterized by a notion of type. So you would like to be able to take pairs of simply typed signatures, so a type system, with a model on it. The issue is that in all of these signatures here, well, you actually have a lot of garbage. You have all the signatures you could imagine, even signatures that you cannot eliminate to. And if you can't eliminate from a signature to the other, why would you care about it for a recursion principle? And we have a nice solution for that, is just take the co-slice. So basically, it literally means you keep only the signatures that you care about, only the one you can eliminate to, because an object in the co-slice is just a signature such that there's a morphism to it. And then you can restrict your functor even more because you just got rid of more object. And well, once you've done that, you have a very, very nice result that tells you that if something is initial here, it's nice, it's your initial signature, and its image as an initial object, then you can take the Grothendieck construction of this, which is basically a sort of sigma type, and you're going to end up having a category, and your object is going to be initial in it. So what it means is that you can now just take using this functor, define an object as a model over simply type signatures, equipped with the associated notion of morphism. That's going to be morphism up to retyping. And in this extended category, this generalized category of models, the initial model of your signature is going to be initial. And so what it means is that before we had a category that was an erection principle that was like limited to one type system, and here everything has become parametric by the type system. And so this is not strictly using two-functoriality, because I guess you could use that this is only a one functor, but it's very nice to just have like one result, two-functoriality, and just restrict it on the left to be able to take a bigger category. So as a sum up, basically we've presented a generic method to compare models of a different base category. And I think it can be nicely packaged in the slogan, models are two-functorial, which means if you have relation on your base category, then you can leave. And also importantly, doing so, we close a gap in the literature, because in all the papers by Fiore, Hirschowitz, or people like that, they have all basically used different base categories. Fiore has always used F-set, whereas André or Tom Hirschowitz have mostly used set-to-set. And while there was a bit of work on the subject to relating it, it was very ad hoc, and now we have a very nice way to relate them. So voilà, thanks.
Questions?
Thank you, nice talk. As you certainly know, there is this other approach to abstract syntax through nominal sets. Does this fit into your framework also?
So it's really a question I get often. I haven't really explored this literature. According to Ambroise that contacted, sorry, I forgot, is it Hoffman? I think Hoffman has a paper on this in 2007, and he told us that not many people have actually worked on the connection, but apparently there's the PhD of Sam Staton that would tackle the problem and would say it's basically the same up to having pullback in your base category.
Sure, that's clear. That's clear. But the question is, can you capture this connection in your two-categorical setting? Can you formalize it?
Formalize it? Do you mean in a proof assistant?
Yeah, in two categories. Yeah.
Ah, in two categories? Yeah, I'm hoping so. I don't see why it would be problematic. I haven't done the math, but...
Okay, would be nice. Thank you.
Hi, Max New, University of Michigan. So I have a question about this two-functoriality aspect, because when I think of the simply typed lambda calculus, the universal property of it, say for Cartesian closed categories, that it's initial, that would also be a weak kind of initiality property, right? That the functor you get out of the simply typed lambda calculus is only unique up to some kind of equivalence of Cartesian closed categories. But that's not, am I correct that that's not the kind of universal property you're considering for lambda calculus here? This is the universal property for the lambda calculus here is a one categorical universal property?
Yes.
Like you're saying the lambda calculus is a theory in your, or signature, and then it's an initial object, the lambda calculus, the syntax.
Yeah, exactly. You can definitely see it this way. Here it's really like initial semantic in this trend is really a way to say, give me a base category, set DCPOs or whatever, and I will give you an initial object. And then you have like your models, which is just a category over this base category. So by design, you're fixed into one base category, and you are really lacking a way to change base categories to relate from set to DCPOs, which you wouldn't have an issue if you're already kind of two-categorical as with Cartesian closed categories.
So you're saying you wouldn't have this issue if you were considering it as a two-categorical universal property for lambda calculus? Or would you need to have a three-functorial story about your models in this case?
Honestly, I'm not sure.
Okay, I'll talk to you later.
Yeah, we need to see it down.
Okay. Okay. Then.
Can you do substructural binding?
Also.
Like linear logic?
Yeah, I mean, there's definitely instantiation of that. I don't really see what's the issue. Basically, linear logic is only linear because of typing. I mean, it's because your rule is additive, additive and not multiplicative. But I don't remember which one. That it's linear. Otherwise, it's just constructor and syntax.
So you're saying you could have a theory for linear lambda calculus instead of simply type lambda calculus?
Yeah, I think so. No?
Has this stuff that you have a diamond and you have a fine and linear and like fully structural, and you also parameterize by an arbitrary monoidal category for the base category, right? So
yeah.
It should cover it. Yeah.
Oh, very cool.
But actually, there's a paper that's interesting by Ambroise at Popol 2020 or something, where he considered an addition of this with reduction rules. And so he defined the lambda calculus with explicit substitution and show it compiles to the regular lambda calculus, showing that the semantic is preserved. And so it's funny because you really see that in your source, you're using like a one-step reduction, but to be able to be reduction safe, you actually need to go to the transitive closure. So you do have like work like this where you can be really fine. There's even like strategies, and or you can formalize even sequent, like the typing derivation associated to syntax. So it's actually quite powerful. You just can't do what Ambroise likes, which are SOGAT and dependent binders.
Can I also ask a question?
Sure.
So your signatures, are they independent of the base category, or in certain cases they depend on the base category?
Yeah, definitely, because en fait, for instance, if you look at this thing, voilà.
Like if the base category has types, then you need to include some types in your signature as well, right?
No, actually, it's not how it works. En fait, you have a very broad notion of signatures and very nice properties, like, oh, if my base category is complete, then my notion of signatures is going to be complete, and so on. So it's really fully abstract. And if you work with a particular instance, like set power t to set power t, then you have to explain how do I define bindings for this base category, because of course binding is different if you're untyped or typed. So here you really have a fully abstract notion of signatures, and it's when you instantiate it that you actually have to define a signature and prove it verifies the initiality theorem.
Yeah. And your signatures, are they like Lovier style, so presentation independent? Like, can you extract the number of operations from the signature or some syntactic information like this?
I mean, not so much. This is really a framework that's meant to be instantiated. So everything is like models, like a signature is literally like a functor.
Yeah.
So it's very fully abstract. You don't get anything out of that. But in real life, you just build a signature on an instance out of product, so coproducts for the different constructors, and so on. And for instance, if you want to bin moncat and captures untyped variable binding, you're just going to need a power object or x+1 operation.
Mm-hmm. Yeah. Okay, thanks. Okay, let's thank the speaker again. Second talk of the session is by Henning Gurbat on bialgebraic reasoning for stateful languages.
Okay now? Hello? Does it work? Hello? Yeah. Okay, fine. Yeah, great. The marvels of modern technology. Okay, great. So yeah, this talk is about something completely different, namely not about types. It's about the fundamental problem of reasoning about equivalence of programs, in particular in the context of languages with the notion of state and variable store. And because it's more fun to do this using category theory, we want to use category theory to do that, to achieve a more fundamental and basic and principled way of reasoning about this. So let me try if I get to full screen. Okay, doesn't seem to work. Yeah, so let me start with a very simple toy example. So we take our textbook Y language that you see in every introductory course on programming languages, and I ask, are these two programs equivalent? Do they do the same thing? So the first one puts x to 10 and then decrements x until it reaches 0, and the second one puts x to minus 10 and then increments x until it's 0. So are these programs equivalent? Well, that's a nonsensical question because I didn't tell you what equivalent means. And in fact, there are various ways to answer this. So if you take your standard big step or natural semantics, that we also like to call termination semantics, then they are equivalent because they generate the same final state, namely at the end in both programs x is 0, right? But you can also, for example, look at cost semantics, which means you not only take the final state, but you also take into consideration the number of steps to reach it. And in this case, both programs take 10 steps, so they are also cost equivalent. But another sensible notion of semantics is trace semantics, which means you consider the sequence of states generated by the program. And in this case, obviously, the sequence of states is not the same, although the final state is the same, right? So they are not equivalent under trace semantics, right? So this is, these are notions of semantics that we would like to reason about. And a nice property of each of these three kinds of semantics is that they yield a compositionality property, namely, if you take two equivalent programs and put them into any context, for example, into the context of a while loop, then these two more complex programs remain equivalent. So this is called compositionality, and it means that you can reason about equivalence of programs by just looking into simpler subprograms, which is obviously something that you want to have and that every good notion of equivalence should satisfy. And yeah, this is the kind of theorem that we would like to reason about at an abstract level. And why do we want to do this? Well, the proof of this kind of statement is obviously, if you state it like this, specific to the language and also specific to the notion of equivalence. So even for the simple Y language, you would really have to give 3 different proofs of this theorem, which is doable for the Y language, but if you talk about languages that are more complex, that have features like higher order store, for example, or functional features, this can become really complex very fast. And so we would like to go for a more uniform approach. And the approach that we take is a Bialgebraic approach that is based on Turian-Plotkin's abstract GSOS, which I will recall in a minute, and on its higher order extension that we recently developed in a series of papers starting at Popple 23. So, so what is abstract GSOS? This was developed by Turian-Plotkin in the late 1990s, so it's a quite classical approach to reasoning about equivalence of programs using category theory. And what they did is they started with the observation, so what are the ingredients of a programming language, like the Y language? So typically, you have a syntax, so you have a specification, some grammar that specifies which terms you have. You have operational rules that explain how the programs evolve. So in this case, rules that explain how programs transform the state. The state, in this case, just being an assignment of variables to integers, so very simple. And these rules induce an operational model, which is a kind of transition system on the set of programs. So in this case, you take a program, you take a state, and then you either move to another program and another state, or just to a state terminate, right? And the key observation by Touré and Plotkin was that you can abstract all these ingredients in a very nice and natural way. Namely, the syntax, as we just heard in the first talk, can be modeled as an initial algebra for a suitable signature functor. So in this case, it would just be a functor on set, but for example, if you talk about a lambda calculus, it would be a functor on some presheaf category or nominal sets of some kind. The operational model can be then abstracted to a coalgebra for a suitable behavior functor B. So it's just a coalgebra on the set, on this object, mu sigma of program terms. And crucially, the operational rules can be modeled using this notion of a GSOS law, which is a natural transformation of this kind. And the idea is that this is a function that encodes the rules into a family of maps. So what this map says is, you give me some operation from my language, like sequential composition. You tell me for each of the operands what its one-step behavior is. So in this case, for example, I tell you from P and S I can go to P prime and S prime. And then I tell you where to transition into next. So the sigma star here is the free monad, so you can transition into arbitrary terms. Yeah? So a GSOS law is just an encoding of a set of rules into a family of natural functions. And yeah, this is really the key idea by Touré and Plotkin. And what they showed is that at this level of abstraction, you can actually reason about program equivalence. They have a compositionality result that says, in any of these settings, strong bisimilarity on this coalgebra of program terms is always a congruence, with a categorical notion of congruence that I will not state here, but there is a categorical abstraction of saying what a congruence is. So this looks very useful. It's a compositionality result for free, but unfortunately, in the context of stateful languages, it is completely useless. And this is because it talks about strong bisimilarity, and strong bisimilarity on this set of while programs corresponds to what is called a resumption semantics. And this means that you have an observer that can, at any point of execution, read the state and also modify the state. So, for example, if you take these two programs, the first one sets x to 1 and then to 2, and the second one sets x to 1 and then increments it. I think every reasonable person would say these should be equivalent, but they are not under resumption semantics, because if you take an observer that after the first step sets the state to something else than 1, say 3, yeah? Then after the second step, the first program is still 2, but the second one would be 3 or 4, right? So by interfering with the state after the first step, you can distinguish these two programs after the second step. So they are not equivalent under strong bisimilarity. In fact, it is difficult to find any non-trivial examples of equivalent programs under strong bisimilarity. And so while we get a compositionality result for this, it's not really useful because it's far too fine-grained semantics. So we want trace, cost, and termination semantics, right? And yeah, people have thought about this problem. There is a series of papers by Abu Saleh and Pattinson from about 15 years ago, where they develop abstract GSOS theory over Gleisli categories for state monads. It's quite a complex theory. And what they can do in the end is cost semantics in this setting, but not trace and termination semantics. And what we propose here is something that we think is an improvement of this. Namely, it is developing abstract GSOS over 2 sorted sets, so a much simpler setting. And it covers all 3 kinds of semantics. And in the rest of the talk, I'm going to explain briefly how this works. And yeah, the key idea is to divide programs into 2 kinds of programs, namely readers and writers. So a reader is like an ordinary program, so it expects a state to be given and then just runs it. And a writer is a running computation. So it's a program that already has a state and eventually might produce new states. And before going into the syntactic details of how this is implemented, let me see what we want to achieve with this. So the operational model of the while lag already has a state then. And a writer can either produce a new writer and a state, or it can silently transition into a new writer, or it can terminate in a state. 3 different kinds of behaviors. And the nice thing about this two-sorted structure is that now one can see that trace, cost, and termination equivalence correspond to forms of co-algebraic weak bisimilarity. So for every coalgebra of any type, you have an abstract notion of weak bisimilarity. This is something that the theory of coalgebras gives you. I will not go into technical details here, but these notions exist, and they are parametric in what is called a relation lifting. And by choosing different relation liftings, you can basically make a choice that you can ignore silent transitions, or that you want to ignore intermediate states or combinations of these. And then you can model, in particular, these 3 notions of program equivalence in this two-sorted setting. Yeah, so this is good because it means that we get a handle on these different notions of semantics using a co-algebraic concept. Yeah, and now I just have to explain how, in the case of the while language, this is implemented. And here's how it's done. So a reader is just an ordinary while program. So the syntax is exactly the same as before. And a writer is one of 4 kinds of programs. So we have this term called bracket PS, which is parameterized in a state. So the state is part of the syntax here, and intuitively should behave like P given the input state S. Yeah? Then we have a term called S.C, which says output S, then behave like C. Then we have a term read S that should output S and then terminate. And then we have another kind of sequential composition that says run C until termination, and then run the reader queue on the initial state of C. Yeah? So it's quite a simple kind of extension. And so what does this do semantically? Let me explain it in an example run. So here you have a run of your standard while language. So it's this loop that we have already seen. And what you would do is typically you would unfold, you take the first x to x minus 1 out, and then output the state 10, and then do this decrement, and so on. Yeah? So this is how you typically run while programs. And in this extension, you do it in a more controlled way, but in the end, you output the same sequence of states. So we start with this program, and in the first step, we will basically pull out the x equals x minus 1 and tag the program with the current state. Then we output the current state. This is what this dot operation does, output the current state. Then we pull the tag into the x equals x minus 1. This is a silent transition, nothing happens here, no output. Then we actually execute the decrement. So now the program is turned into read x minus x1. So and read x9 means output the state x equals 9, and then continue in this way. Yeah, so this is basically equivalent to the previous program. We output the same sequence of states, but we do it in a more controlled way, where at every step we tag the subprogram that we currently evaluate by the current state, and then do the output. Yeah, so it's just a more convoluted way of writing the ordinary evaluation of a while program. But, as I said before, now we do this in this two-sorted setting, and therefore we can talk about trace, cost, and termination semantics in this setting. And so we can hope that at this level of generality, we should be able to get a congruence result for equivalence of programs. And in fact, we have this. So I mentioned this result by Turri and Plotkin, this nice but pretty useless result about strong bisimilarity. And there is a generic result about weak bisimilarity as well in the setting of abstract GSOS that says if you have a sufficiently nice language modeled in abstract GSOS, then weak bisimilarity on its operational model is a congruence, where weak bisimilarity here, as I said, is parametric in a choice of a relation lifting. So you get different notions of weak bisimilarity by different choices of liftings. And being nice means that the rules of the language are polymorphic and they respect weak transitions in a suitable way. And you can make this formal using diagrams, what this means. So we have this result, and now we can just apply it. And we get the compositionality theorem for while that I showed at the beginning of the talk as a simple corollary of this generic result about weak bisimilarity for stateful languages. So, of course, what is not so interesting is the fact that we get this result, that we get this corollary, but that it's generic. So we get it by just choosing categorical ingredients and get this result almost for free. And what I should mention here at the end is that this is, of course, a principle. Yeah? So I showed how this works in this very simple-minded while language. But in principle, you can apply this to every kind of stateful language. Yeah? You just take any stateful language, you do this reader-writer decoupling with these artificial operations that tag programs with the current state. And in particular, you can, for example, apply it to higher order languages. And this is also something that we did in the paper, and I don't have to have the time to go into details here, but in this recent work, we developed this theory of higher order abstract GSOS, which is GSOS for higher order languages, based on the very simple idea of replacing this behavior endofunctor by a suitable behavior bifunctor that is contravariant in the first component and covariant in the second component. And maybe I can give you the gist why it's a bifunctor. Let's go back to the first slide. So here is the functor for the Y language, and you have this to the S in the exponent, the W to the S. Here the S is just a constant, so it's just an endofunctor. But in a higher order language with higher order state, the S itself would be dependent on the set of programs, because a higher order state means you can store programs in the variable store, right? And so in the higher order setting, this becomes a bifunctor where the contravariance is because of the component of the exponent. And one can run this abstract GSOS theory in this higher order setting. And what one gets is an abstract theory of bisimulation that is sound for contextual equivalence, and we have worked out several examples of this in the paper, so you're invited to read about this. Okay, thank you.
Questions?
Yep.
Hello, Max New, University of Michigan. So the two I'm trying to wrap my head around the reader-writer distinction. So I remember you had a paper at Popple that was called by push value abstract GSOS stuff.
Yep.
This is not related to the call by push value. It doesn't seem to line up to me, but
no, not right now. So if you, this is just a simple first order language at this point, right?
Yeah.
In principle, you can apply this whole framework.
Sorry, I'm asking, is this distinction related to the value computation distinction in call by push value?
Well, it's a good question. So it's a bit analogous. It's not call by push value, but it's analogous in the sense that you have an explicit translation of readers into writers using this tag notation, right? So in a way, it is in spirit similar, but it's not called a push value.
Right, like the readers include stateful updates, so they're very much not pure values.
Exactly, so it's not the same thing, but it's inspired by the call by push value paradigm. Yeah.
Thank you.
Yeah.
I have a question. So the reader-writer distinction, so that's a more fine-grained language than like the Y language that you showed. So are there multiple ways to add this extra information to the Y language or is there a standard way to do this?
Well, there are obviously some design choices that you can take. It took us quite a long time to get it right. In the sense that the semantics of the extended language is the same in the sense that the output sequence doesn't change of the states. Yeah. And yeah, I would say that there are some design choices, but for example, this principle that you want to tag the states with, so this bracket operation, I think this always must be there. And in the other operations, there might be some choices how you control it precisely. But the first one, I think, is really the fundamental one. This is necessary, absolutely. Yeah.
Okay, one more question. Last question.
Oh, I'll do it.
He had a question.
Okay, then you go. Sorry.
Macquarie University, Jinyang Zhang. I think do you have any plan to extend this system to other effect systems, such as exceptions or any other that kind of effects?
Sorry, what was the last word?
Sorry?
I didn't get the last part of the sentence. Such as what?
Exceptions or such as
sure. So, I mean, obviously, one key goal would be to apply this to effectful languages in general, right? Where you have possibly even a monad as a parameter. We're not there yet, but I think exceptions would be a very natural next step to, if you want to go for a specific effect. But we haven't done this so far.
Okay, thank you. Let's thank the speaker again.
Okay, thank you.
It's fine. Yeah, can you test? Is that okay? So I'm now, should we be able to? Yeah. Should I be able to see my screen? Okay.
Okay. Welcome, everyone. Welcome, everyone. As you know, most of the sessions today are double track, so we have 2 sessions in parallel. That's not the case for this session, because the 4 papers being presented now are the distinguished papers. So every year we hand out 4 distinguished paper awards, and all those are in this session. They are in a single track without something in parallel, because we think they deserve ICFP's full attention. And the first speaker I should introduce is Kimball Germain from Brigham Young University.
Thank you. I'm happy to be here with you. I'm going to talk today about a work called Call-Guarded Abstract Definitional Interpreters. Is this too loud? And to set the stage, I kind of want to talk about a methodology called abstracting abstract machines, which you may be familiar with. But what abstracting abstract machines, or AAM, gives you is the ability to turn a small step formalism, or a formalism of your small step semantics, systematically into a static analysis. And the way you do this is by taking the state space of your formalism and redirecting all recursive structure through a central component called the store. The store is going to come up several times in this talk. And then finitizing the address space of that store. And that, in effect, finitizes the execution space. Now, 2 important properties of a static analysis are soundness and computability. And the AAM framework offers computability very cheaply, because with a finite state space, you can just turn the crank on your analysis, and you're guaranteed that it will terminate. So there's a spiritual sequel, kind of, to abstracting abstract machines, which is abstracting definitional interpreters. And this follows the recipe fairly closely. It's a little more accessible because you express your semantics as a definitional interpreter written in monadic style. But you do the same kind of indirecting of recursive structure, except you do not indirect the stack through the store. And the result is that you get a static analysis which is sound and computable and has high control precision. So I just want to make a little bit of an analogy here, that if we imagine that our concrete semantics is rich in behavior and it's very detailed, and that the static analysis is a necessary approximation in order to be computable. And so it gives us a decent picture of what's going on, but certainly some of the details have been discarded or lost. And I want to illustrate how that can happen with some examples. So this is just a simple example where we have an apply function, where you hand it the function and its argument, it applies them. And it's called twice. And in this program, add 1 will only ever be applied to 12, and sub 1 will only ever be applied to 10. But the analysis that we're considering now is a context-insensitive analysis. And what that means is that every binding to the variable f1 and the variable x1 are going to be mapped in the same place in the store. And that means that there will be 2 values for each. So when the analyzer considers this function call, in order to be sound, it's got to consider every value mapped for those variables. And so the analyzer will associate add 1 with 10 and sub 1 with 12, associations that would never occur in the real program. Now, we can solve this problem by adding context sensitivity. And the way we do this is we pick a notion of context. A very popular one is from KCFA, which is to keep track of the last K call sites encountered in execution. And those serve as your context. And that context qualifies every allocation you make in the store. So you can see here that this store now has 4 mappings. We've got the same variables being mapped, but each one is qualified by the call which affected that allocation in the store. And so you can kind of glean from the store the correspondence between the arguments to apply. Now, when the analyzer encounters this call, the same call, it's going to encounter it in 2 different contexts. And because it has the context in hand, it will look up precisely the variable it needs to, or precisely the value that is. And we will no longer have this spurious correspondence between add 1 and 12 and 10. So what context sensitivity gives us is a little bit of a clearer picture of what's going on with our program. But there are 2 problems with it. The first problem is that the abstracting abstract machines framework applies the finitization uniformly across the program. And when we add context sensitivity, we get the same finitization, but at a finer grain. And the result is that in parts of the picture with detail, we do get a better understanding of the program's behavior. But in parts of the picture that are more uniform, just to really stretch this analogy in the background, we are still paying for every pixel with analysis effort, but we're not getting much more information about what the program is doing. So it's not a useful, or it's not a cost-effective use of our analysis resources. The second problem is that increasing the context sensitivity only happened to work for that program. So if we refactor the program, what I've done here is just eta expanded apply 1 to apply 2. Now we're in the same position we were before without context sensitivity. That is, we make a call to apply 1, and the analyzer correctly keeps track of the context and is able to distinguish between the bindings. But then every call made to apply 2 is made in the context of apply 1, and the analyzer has no means to keep these bindings distinct. And actually, it's worse than the context-insensitive example because we're paying for context sensitivity but not getting it. So to finalize the analogy here, what I have on the right is it's a portion of the Mona Lisa that was constructed using 50 translucent polygons, and it was constructed using a genetic algorithm. And the analogy I want to make is that part of my work is to develop analyzers that are more responsive to program structure so that we get better answers for a given amount of effort. And in some sense, it's unavoidable that our analyzer would be sensitive to program structure. It's a theorem that any static analyzer is going to be sensitive to some intentional properties of the program. But the goal is to be more responsive to the program. And this work is a step in that direction. So now I want to tell you what a call-guarded abstract definitional interpreter is. So it's a hybrid interpreter that contains a full copy of the concrete and abstract semantics. The concrete semantics are completely precise. There's no finitization involved in them. And the abstract semantics are pulled just from an off-the-shelf analysis like KCFA. And the way the interpreter works is that every evaluation is optimistically started using the concrete semantics. And only when the analyzer determines that that analysis will not converge with those semantics does it degenerate to abstract semantics. And so on any given evaluation path, it will continue to evaluate in either concrete or abstract. But when it encounters non-tail evaluation, so for instance, if it encounters like a function call and it's evaluating the arguments, it will revert to concrete semantics on the off chance it'll get better precision. So just a little bit more formally, we've got this state space. And the important thing to see here is that our stores are addresses to values, and the values are either abstract or concrete. So they coexist in the analysis. And we've got this judgment here, this evaluation judgment. The first four terms are familiar from maybe a CESK or a CES machine with a timestamp. The M component is an evaluation mode. So every evaluation of a configuration is done in a particular mode, which is either concrete or abstract. And then the C corresponds to a call cache, which is defined by the call guard, which is a parameter of the analysis. And we offer this theorem that if the call guard satisfies certain properties, which I'll go over momentarily, then the analysis is computable. So the call guard monitors every function call and gets to determine under which regime the function call is evaluated, concrete or abstract. And the condition that it must satisfy is that it must supply an ordering on its call cache with no infinite ascending chains, and it must increase monotonically on any given evaluation path. So the paper describes two example call guards, a reentrancy guard and a size change guard. I want to go over those briefly. So the reentrancy guard uses a call cache that is just a set of function entry points that have been encountered on that evaluation path. And what this allows you to do is maintain concrete interpretation in any tree in the call graph. So if there's no recursion, if there are no cycles in the call graph or in the subgraph that you're in, then you maintain concrete interpretation. So for example, we could eta expand arbitrarily in our previous example and still maintain concrete interpretation. I just want to show a little bit of an example of this in action. So we've got a simple example or a simple program here that will just loop. And what I have on the left here is the abstract interpretation of this program. And as you can see, it converges pretty quickly. On the right, we have the call-guarded interpretation of this program. And so what we've added to each configuration is the mode, as you can see, and the set of entry points. And I just want to point out, if you look at the environments of the abstract interpretation, you'll see that we have variables mapping to variables. In this, we have variables mapping to indeterminate addresses, but these are concrete addresses. And so the analyzer begins by allocating concretely in the store, and then only determines once loop has been entered a second time that it needs to degenerate to abstract, and then finishes the analysis. Okay, so that behaved as we would expect, because we would not want to just kind of go on forever analyzing loop. However, here's an example, factorial, where using a reentrancy call guard is very unsatisfying, because it's fairly apparent that this evaluation is going to converge. And so let's shift and talk about the size change call guard. So the size change call guard is based off of this principle called the size change principle for program termination, and it's this. A program terminates on all inputs if every infinite call sequence would cause infinite descent on values under a well-founded order. And this is from Lee and his co-authors, and the idea here is that if you can characterize the argument descent from a function to the function it calls, the parameters, that is, and then you can compose those characterizations to get an account of argument descent across function calls, then you can use this principle to determine whether the program is guaranteed to terminate or not. And the way that they characterize argument descent is with something called a size change graph. So this program at the top has two mutually recursive functions, and what we have underneath are some size change graphs for them. So on the far left, we've got a size change graph from F to G. So the call in F to G passes its parameter directly, and then one less than one of its parameters. And that's reflected in the size change graph, where we have X has an arrow to A, and it does not descend, but it does not ascend. And then Y has an arrow to B, and this less than means that B is strictly less than Y. So that's a size change graph. There's an alternative notation beneath. And this is how they characterize argument descent from call to call. And you can compose size change graphs, that's on the right, just by following paths with edges, and you get the sort of least strict annotation on the resulting edge as was on those edges, or the most strict, I should say. Now, how do we apply this? So there's some great work by Phil Nguyen where they apply size change monitoring to offer termination as a contract on functions. And basically what that means is dynamically at runtime, they watch function calls, and when a function calls itself, or sorry, when a function is entered and has been called before on that path, they dynamically compute a size change graph of the actual arguments from the previous call and the current call, and they apply this size change condition. So there's this condition that you can property of size change graphs that tells you whether or not there are any infinite ascending or descending sequences. So this is fairly straightforward to cast as a call guard in our framework. And so that's what we do. We have a call guard where we detect when a path violates the size change condition. And the call cache is a map from function entry point to a set of size change graphs. So I won't go through this example in excruciating detail, but on the right I will show that the first time that factorial is entered, the entry point of factorial is mapped to the unit size change graph, and then on every recursive call, we compose the current size change graph with whatever the difference is. And the effect is that this slide, even though it shows a hybrid analysis, is showing just concrete interpretation. So the size change call guard is able to maintain concrete interpretation on this program. So I want to talk a little bit about the ordering we use, the value ordering we use for size change. I'm going to go to the second slide first. So the language that we use is essentially ML. It's got functions, data, and structural mutation. And so the ordering we use on functions and data, let's talk about functions first. they're standard off-the-shelf orderings. So for functions you have that, if you've got a function over the same, or sorry, a closure over the same lambda, but one of its arguments is, or one of its environment variables is smaller, then that counts as smaller. Anyway, the idea is that they're off-the-shelf orderings, but you can modify them if you want. Okay, I'll briefly talk about our empirical evaluation. So we use two sets of programs. We evaluated on two sets of programs. One of them is a standard program corpus for analysis. These were programs crafted to demonstrate the effectiveness of certain analysis techniques and approaches. And the second one is a subset of Larceny R6RS benchmark. And so there's a lot of different behaviors that are exercised in these programs. The result, kind of the high order bit here, is that call-guarded abstract definitional interpreters, the hybrid analysis, was able to maintain concrete evaluation for most of evaluation. So just in interest of time, I'll show you this. So actually, I take it back. Okay. What we're looking at is the results when we look at, okay, so when the analyzer runs, it's in a mode that's either concrete or abstract. And the analyzer in concrete mode may end up getting an abstract result. So we measured how frequently, when run in a concrete mode, does the analyzer get a concrete result versus an abstract result. And we compared that to the corresponding abstract interpretation that is always going to get abstract results. And we kind of compared the number of concrete results we got, and the upshot is that for most of these programs, we were able to keep the interpretation completely concrete. That sort of makes sense for benchmark programs because you would expect those to be deterministic and they specify a single run. It's a little surprising for the programs crafted to exercise static analyzers because it means that using a size change call guard, you are able to just easily handle all of the patterns that that techniques were developed to handle individually. I will skip this. So there's still work to do, obviously. The Ackermann function satisfies the size change termination condition. And so in our framework, it is technically computable, but not effectively computable, or effectively, I guess is the wrong word to use there. Anyway, so we're looking into ways to proactively abstract interpretation to accelerate convergence. And we also want to evaluate on larger programs and kind of see how it behaves under those conditions. Thank you.
Hi, Benjamin Quiring from UMD, Maryland. So this first bullet point is something that I was thinking about. Like, you might spend a ton of time evaluating factorial applied to 42, then to later on add it in your abstraction to top or something and basically destroy your result.
Right.
So it seems like something that you could do is look into the future, maybe using lazy evaluation to delay actually evaluating factorial of 42 until you actually figure out that you need it to be a concrete value to actually do something later on in the analysis. Have you thought about doing something like that?
I have not thought about that specific technique. That's an interesting idea.
Let's talk more after then.
Yeah.
Hi, I'm Jay Lee from Seoul National University. I really enjoyed your work. I enjoyed reading the paper as well. I have a small question about the size change detection. So does it work for arbitrary like integers, or do you assume that the domain is just natural numbers?
It works for integers, but our measure is then on the magnitude of the number.
Oh.
You have to ensure that it is a well ordering.
Okay, so even if it's like negative numbers, it should be increasing towards 0.
Yeah, I mean, if you admit integers, then you use something like the magnitude, yeah.
Okay, thank you.
Yeah.
Hi, I might have missed it, but what happens if the main function takes an external parameter?
Oh, I didn't talk about that. The paper does, but in many instances, you're able to still maintain concrete control, even though abstract values are flowing through. Once control depends on an abstract value, you degenerate to abstract.
Okay, so you can be in a. This sounds a little bit like you're in a mixed mode, right? Where
Yeah.
part of the values are abstract, but then not all of them, and you keep on going concretely as long as you don't read from them.
Yeah. So if you think of like the map2 function, that it's map, but it takes two lists. One of the lists is abstract, the other is concrete. It'll follow the concrete one and give you perfect precision following that, even though there's an abstract value that it's sort of looking at too.
Okay. Cool. Thanks.
Okay, so this might be a little bit of an ignorant question. How does this compare to concolic execution?
So concolic execution, good question. As far as I understand, concolic execution is not intended to be sound. It's a way to just combine dynamic analysis with symbolic execution. And sort of a design choice from the very beginning of this was to achieve soundness and computability, but there are probably deeper connections to look at there.
So maybe there's time for one last question while the next speaker starts to set up. Last question?
So you did this for the abstracting definitional interpreters framework, but have you thought about trying to reapply that back to the small step world?
Not seriously.
Okay.
Okay, let's thank Kimball again. So the next speaker is, and I'm trying.
Is it working? Okay. Okay. So thank you, and I'll present my work, Effectful lenses, there and back with different monads. So let's start by considering a motivating example. We know that lambda expressions can be encoded in either using variable names or using the de Bruijn indices. So these two representations are equivalent to each other, and you can convert between them freely. So here we consider this challenge to design a bidirectional converter between the two representations. So if we are converting from the left to the right, that's the usual algorithm apply, and you can just do it the usual way. But if we consider the conversion from the right to the left, that is from nameless representation to the named representation, then we have a problem because there are actually infinitely many different names you can use for the binders due to alpha equivalence. So the challenge here is to recover the names exactly as they were when we are converting from the right to the left. So as it turns out, it seems very obvious that it should be an use case for bidirectional transformations, or lenses as we know it. So we have two different data structures, one called the source and the other called the view. And we are doing synchronization between the two. So here the source is named and the view is the nameless. So there's this forward transformation called get, converting from the source to the view. And after we get the view, we can apply some addeds to it, and we can try to convert it back. But as we have already discovered, this conversion does not work because there is not enough information for this conversion back. So instead, alongside the modified view, we also take the original source. So when we combine the two pieces of information together, we can get an updated source. And the conversion back is called the put component. And get and put together form a lens. So is the problem solved? No, actually, because in this specific challenge, there are some monadic effects required in the conversion process. So for example, consider this pair, this F binding, this F use side and the index 2. F corresponds to the index 2 because we know that F was bound outside here. So in order to use this information, we need to maintain a context, which requires using the reader effect. And let's also consider this example where I used this unbound variable y. So we cannot directly convert this to the right-hand side because we cannot determine a proper index for y. So in this case, we want to report a failure, which requires using the array effect. And finally, let's consider if we start with a nameless on the right and we directly convert back to the left, which means the names are unspecified. And we might want to ask the user for the names. And if we want to do that, we need to interact with the user, which requires using the I/O effect. So these are all the potential effects we want to use for this conversion process. And it turns out that the traditional lens framework does not support monadic effects. So the problem is to combine lens frameworks with monadic effects. So there are some very useful properties comes with lens frameworks. Like we have a correctness specification for lenses such that we have exact recovery when we are converting from the view to the source. And we also have consistency between the two directions of the conversions. And the lens framework also supports compositional programming, which means we can combine smaller programs into larger programs using various combinators. And we want to maintain these two strengths for the lens frameworks, but introducing the effects into the picture, which we want to use, for example, these 3 effects. So let's first consider the 2 strengths for pure lenses. We have this correctness specification, which we call the round-trip properties. They specify the correctness or consistency between the 2 directions of the conversion. So the get-put property states that if we get, and we get the view, and we do not modify it, and we directly put it back, we should get back the exact same source, which means exact recovery. That's our requirement previously. And the other way around, if we first put and then we get, we should get back the view we just put in. So that it means all the information in the view should be reflected in the source. And this entails the consistency between the 2 conversions. And for compositional programming, one very important thing about lenses is that they can be composed, which means we can chain lenses into a pipeline. So if we have a lens F between X and Y, and we also have a lens between Y and Z, then we can form this lens G after F, which is between X and Z. The important thing about this composition is that it preserves the round-trip properties, and this is key to compositional programming. So if we look at the previous works, we see this is a known problem when we combine lenses with monads. So you might just think that we can just do it by introducing the monad M into the 2 return values, the return types of get and put, and we get this naive encoding. And then we discover that when we try to define a composition, it becomes very problematic. We can still define it by directly generalizing from the pure definition for lenses, and we get this definition. But when we consider their composition, for example here, first get followed by put, and we expand the definition for get and put respectively. So if we want to show that composition preserves the round-trip properties, the goal is to show that the get-put of this composition follows from the get-put property for both F and G, which means we want to find a substructure for get-F followed by put-F in this composition chain. And if we look at the right-hand side, we see this structure where we have this extra get-G in between. So it means that we cannot actually apply the get-put of F to simplify this expression. And all the reasoning are stuck, and we're out of luck. So in the previous works, it is decided that the problem is that get is impure. So they make get pure by removing the monad m from get. And in this case, if get is pure, then due to referential transparency, we can just show that composition really preserves the round-trip properties. But that does not apply to our motivating example because we really want to use effects in both of our directions. So the first question is, can we allow impure get? Okay, and the second question comes from the semantics for the round-trip properties. So if we directly generalize the get put property from pure lenses, we specify that this in terms of get followed by put is equal to pure. Then on the left-hand side, get performs some effect here. But if we consider right-hand side, there's no effect in the round trip, which means the effect of get is somehow canceled by put. And recall that we want to use effects like error and IO, and they cannot be meaningfully canceled. So our second question is, how do we support non-cancelable effects? And finally, recall that we want to use IO to interact with the user input. But on the other hand, get does not have access to IO. So we should be able to use different monads in get input. And the question is how? So when we really use different monads in get input, we see that the monadic length composition itself becomes invalid because the definition previously shown uses get input. And it becomes invalid because those are using different monads. And also, we need to find out a way to describe the interactions between the two effectful computations, which use different monads. So the plan for the rest of the talk is to address these questions. And as it turns out, the definition for lens are key to solving questions 1 and 3. And the round-trip properties are there to solve the last two questions. So first, we consider a definition. We discovered that we can solve the questions by migrating from the previously shown encoding for lenses to this well-known representation of lenses called lenses with complements. And they are known to be equivalent to each other. So still we have the source and the view. We can convert from the original source to the extracted view by using GAT. And then this conversion discards some information, so we cannot directly put it back. But instead of taking the original view, we require that the forward direction computes something called a complement alongside the view. So the complement saves the lost information in the forward transformation. And then in the backward direction, we can combine this complement with the modified view to get back the updated source. By using this structure for lenses, we see that in the definition for the composition, the two directions get and put are cleanly separated. So question 1 and question 3 are addressed. Now we can consider this definition. This is definition for pure lenses with complements. We just add the two monads M and N to lenses with the complements. And we define the composition by directly generalizing the pure definitions. And then we consider the round-trip properties, which are the correctness. We see that the round-trip properties for pure lenses are actually specified using function inverse. So we generalize invertibility relation to what we call the round-trip relations. We have this relation R between the two Kleist arrows to describe something which is a generalization of F after G is ID. And based on this round-trip relations, we add the extra logic to handle the complements, and we get the round-trip properties for lenses. And it can be specified using a pair of round-trip relations because we have two different round-trip properties. And then the other two questions are addressed. So based on these definitions, we can start to build a rich combinator language for the user to construct useful programs in our framework. And as it turns out, the monads M and N and the round-trip relations, they are specified by the user. But we want a general theory that can be used for whatever effects the user might choose. So for example, we want some combinators like ID and composition, which provide a category structure for lenses. And also we want product and sum, which supports polynomial functors. And finally, we want something to support manipulating the complements for the lenses. And all of these combinators should work regardless of what effects the user might choose. So our solution is to specify a set of axioms, these 5 axioms, to bridge between the two lenses. So as long as the round-trip relations the user specified satisfy these 5 axioms, all of our combinators would work. And now let's get back to the motivating example and see how we solve it. So an important lesson is that program structure should follow data structure, right? So we first consider the data structure to be synchronized, which is the expression here. As we can see, it is a recursive data type. So the first thing we can do is to apply some recursion scheme to reduce it to a polynomial functor. And the polynomial functor has a sum of product structure. So we can first use some combinators for sum, which breaks down into 3 different branches. And then for each branch, it is a product structure. So we can use the product combinators. So here's the actual code for the example. First, we choose a monad to describe the effects used in the example. Here, I combine the reader and the error here. And we also choose the round-trip relation for this monad M. And here we see the top-level converter is converting between the named and nameless expressions. And we use the recursion scheme here, so we get the algebra for the recursive conversion. And then we consider the algebra. As I have just said, it's in the product of sum, sum of product structure. So we apply sums here to reduce it to 3 branches. And for each branch, we can define the lenses. So we can use other combinators in constructing these different branches. So to conclude, we present the first lens framework with different effects in get and put. And it is based on the alternative encoding for lenses, which is called lenses with complements. And we propose using round-trip relations to describe the interaction between the 2 different effects. And the round-trip properties are then built on top of the round-trip relations by adding the extra logic for complements. And the framework supports compositional programming by saying that all of our combinators preserve the round-trip properties. And finally, we have this case study. So there are actually 3 different flavors for this converter in the paper. So if you are interested, you can check it out. And the last thing I want to say is that all of our theory and the examples are implemented and verified in AGDA. So that's all of my presentation. Thank you.
Questions? So I had a question already. Maybe if you could say a bit more about these round-trip relation. Can you show an example of what that looks like? Or?
Oh, right. OK. So there are some examples in the paper, but I can briefly describe how it works for effects like reader or error. So if we consider reader, what we want is that the same context is used for both directions. So the actual definition is that we run the reader, we interpret the reader effect by supplying the same context S to both directions. And then we either use another relation for the base monads, or we just directly for identities, then, sorry, it might be too complicated. Let's just consider the array effect. So it basically says if the forward succeeds, then the backward should succeed, and it returns the same value. So it's like the forward should be OK, and then backward should also be OK, and it should return the input value x, which should be the same as the original input. So it's really that for each effect we want to use, we specify several different potential round-trip relations to describe the semantics you want. Yeah. I don't know if it answers the question.
User chosen.
Right, it's specified by the user.
Okay.
Very intriguing work. I'm just trying to understand your response to question 2 about supporting non-cancelable effects.
Okay.
As I understand it, your contribution is that you have reduced it to a law that if you've got non-cancelable effects, they have to satisfy. Is that correct?
So the way that we support non-cancelable effects is to delegate the responsibility to the user, right? Because if the user want non-cancelable effects, they can describe what they want with these effects by specifying these round-trip relations. So
Okay.
this relation captures how the effects should interact with each other.
Right. Have you looked, instead of, like, it's a related question, like, for instance, what monads support cancelable effects, right? Like, for instance, you have given an example of logging as an example of a non-cancelable effect, but the logging, or the so-called writer monad, if it was not just if it were not just a monoid, but in fact it was a group, then you could basically append a negative log to cancel the stuff in the log, you see. So have you looked at monads that are cancelable?
So I guess, yes, there might be some monads that can be canceled, but the point is that we want a framework that extends to both things, right? It doesn't only support non-cancelable effects, it also supports other cancelable effects. So in fact, if your effect is cancelable, you just, like, for example, if the get input are using the same monad, you can just use a class decomposition to compose them. And your round-trip relation would be very easy to specify that RFG is just that F, classically fish, G is equal to pure. Mm-hmm. And that's the way you specify the round-trip relation for cancelable effects.
Something else I was wondering about, have you looked at other prisms? So, for example, these lenses that sort of give you a view on multiple copies of the same structure? Or?
Right. So all the other, like the optics or the prism, the traversals, and all the other in the hierarchy, I think that there might be some incompatibilities between the two because the fundamental encodings are relatively different. We haven't really looked into all the other variants in the optic hierarchy, but it might be an interesting thing to look in the next step. Yeah.
Okay. Last chance. Okay. If not, then let's thank Rufeng again. Okay, so the next speaker is Anton Lorentzen from University of Edinburgh, who will tell us about first-order laziness.
All right. Yeah, thank you very much for this introduction. Yeah, so I'm Anton Lorenzen, and I'm presenting this work, which is done in collaboration with Dan Lijn from Microsoft Research, Botte Swistra from the University of Utrecht, and Sim Lindley from the University of Edinburgh. And so the title of our work is First Order Laziness. And to start talking about what first order laziness is, I want to first contrast it against what I call higher order laziness. So this is how you would normally implement laziness in a strict language like OCaml, for example, or in this case, Coca. You have one type, func A, which is usually left abstract, and it has two functions, delay and force. So delay takes a closure that goes from unit to A, and force takes a func and gives you the result of the closure. And so the important thing about this interface is that the delay function only stores the closure and does not run it in particularly. But then force will run the closure once the first time it is invoked and memorize the result afterwards. And so these are the two things that really make up this lazy interface, is that the function is evaluated only once you actually call force, so you can kind of delay a computation, and that the result is memoized for all future calls for force. And we'll come back to these two principles later. Now, let's look at one concrete example for how you would use this interface, and I'll consider streams. So a lazy stream is some stream type A, and you have an scons constructor for like one element on the top of the stream, and you can also append two streams lazily. And so what you can do with this interface is that you can, for example, create a func that will run an sappend between two streams, one stream that has a 1 in front and then has some unknown S1, and I append this on top of S2. And what most programming languages do if you run something like this on the console is that they just tell you, oh, this is a func, but I maybe don't really know what it is. And now, of course, you can force this stung, and then you can see, okay, I'll do like one step of the append function, and I'll see it's an scons 1 in front, but I still don't really know what's in the rest. And so we'd maybe like to look into it. We'd maybe like to say, oh, actually, at this point, like if I've done like one step of the append, I'll still have to append S1 to S2. But usually this is not really possible. And really the reason it's not possible is that this delay thing is a closure, and most programming languages can't really print closures. So So the question I want to ask in this talk is, should laziness be higher order? Because if you think of this delay function, it really, like this idea that you need to supply a closure is really built into this interface. You can't, for example, like supply a constructor or something. And so the fact that delay must take a closure introduces a lot of weird effects. In particular, it makes it a lot harder to reason about the laziness you have, both for the programmers and also the compiler. So in particular, the closure you have in the func can usually not be printed on the console. You don't also really know whether a func has been evaluated yet or not, which makes it a bit harder for you to reason about the performance of your program. But even if you can reason about the performance, it may not actually be that good, because this delay function will actually incur two separate new allocations, one to create the outer func, and then a second one to create the closure that you put into it. And so, I mean, I work a lot on something called Percy's ratio in this talk, is that we can solve all of these problems if we take a new approach to laziness. And the idea is, what I want to do is I want to defunctionalize the laziness from a higher order to a first order representation. Let's look at how that works. So let's actually implement the stream data type. So we have a stream of A's, which consists of an scons constructor that has a head and a tail, and a nil. And so you can see that at this point, it's very much isomorphic to a list, and we'll now add some laziness to it. And the way we do this is by a new language feature that we call lazy constructors. So we'll create a new constructor, sappend, for a lazy append that we want to do between two streams. And so we write this lazy keyword in front to show that it is a lazy constructor. And the important thing you need to do with a lazy constructor is that you need to give a definition for it, which I've done here. And you can see that this definition kind of follows the normal append function you would write. I look at whether the first stream is a cons or a null, and then if it's empty, I'll return S2. And if there's some more, I'll return the first element of S1, and then keep appending. So how do these lazy constructors work? If you create a lazy constructor, it works very much like a normal constructor. So in particular, if you create a new lazy constructor like sappend, it is just a normal value, and nothing much happens. The important thing is what happens if you actually match on them. So in the normal traditional interface, a lazy thunk is evaluated by force. But lazy constructors are evaluated by matching on them. So to look at an example, we can consider the length function. So the length function of a stream is very much like you would imagine the length function also for a list to be. And let's evaluate the length of a lazy constructor that consists of appending the stream 1 in front of S1 to S2. So the first thing we do is, of course, inline the definition of length, and we see that the first thing we do is actually match on the stream that we've provided. And you can see that there's something that doesn't quite work because we do not actually match on the lazy constructor. We only match on constant nil. So how does the compiler do this? The idea is that the compiler now looks up the definition we have in the stream, and in particular looks up the definition of the lazy constructor to rewrite the lazy constructor to this definition. So what we'll do is we'll turn the sappend that we were matching on into the definition where we first destruct the first argument of sappend and then either return scons of sappend or just S2. And now, of course, we can evaluate the inner match, and we just get a match of scons 1 on sappend S1 and S2, which just by the definition of length evaluates to 1 plus the length of the rest of the appended stream. Right. So we can see that the first part of laziness actually happens here. We evaluate lazy constructors on every match. The second principle of what laziness has to do is about memoization. The result of a lazy constructor should be memoized on all future matches. So in particular, let's say I have my lazy constructor here and I bind it to the name S. Then if I perform a match on it, it has to be evaluated to a cons. And after that, it stays evaluated like this. So again, the memoization is happening here, which in particular means that, for example, we can actually model the original delay interface using lazy constructors. So what we'll do is we'll have the stream data type, where we now add one extra constructor that I call sDelay, that takes a closure f from unit to stream A, and the definition is just to invoke this function. So the way I would implement delay now is by just wrapping the function f into an sDelay, and the way you would implement forcing is by matching on the stream to actually evaluate it to one of the regular constructors. Now, the reason why this is such a nice thing is because it means we can apply lazy constructors in our program exactly when we want them, and we're not really forced to make any lazy computation into a lazy constructor. This is in particular important because defunctionalization can be a whole program transformation, but this basically allows us to make lazy computations into lazy constructors if we want to, and we get a benefit from them, but we don't have to do it if we feel like it would be too involved. But of course, sDelay also provides no benefit over the interface we've had before. So I want to talk a bit more about what really the benefits are of having a lazy constructor in this special interface versus having like this general delay interface. And one of the benefits, I think, is that you can kind of peek under the hood a bit to understand what your lazy program is really doing. And in particular is we have a new language feature that we call lazy match that allows us to inspect for a data type which lazy constructor it is. And you can use this, for example, to implement a show function. So if we want to show a stream on the command line, we might want to see where there's still an append happening. And the idea is that we can use lazy match to figure out is this an sappend constructor or not? And if so, we just print the sappend directly on the command line, which is kind of gives you the nice printing behavior that I've shown you before. And I think this is actually really good for debugging in practice if you program with these data structures. But I also want to kind of caution a little bit. So one of the really big benefits of laziness is something called referential transparency. And lazy match breaks referential transparency. So the idea is that this memoization that happens in laziness should be an unobservable side effect, in the sense that the semantics of your program does not allow you to see whether a thunk has been forced or not. And of course, if you show a stream with some appends in there, and then you take the length of the stream, that you will fully evaluate it, and suddenly, if you show it again, it will look very different. So the lazy match does break it. But however, the regular match actually does preserve the referential transparency, because the regular match only lets you look at actually the normal strict constructors and does not allow you to observe the lazy constructors. So, which means that actually if you're very careful in your use of lazy match and maybe only use it for debugging, you actually still get all of the normal reasoning benefits of laziness, even with this approach. Now, I want to talk a bit more about lazy match, in particular because it is very useful also to implement lazy constructors in a good way. And so how would we actually compile something like the stream data type in the compiler? And the idea is that we basically generate an evaluation function that kind of takes a stream and will give you an evaluated version of it back. So the thing we do on the stream in this evaluation function is we lazy match on it, and if it's a nil or a cons, we just return the nil or cons. But in particular, if it is an append, we'll have to use the definition of the lazy constructor to evaluate it further. And there's a few things here. So in particular, append can return this S2 in the end, which again might be a lazy constructor. So what we're doing there is we're actually writing an indirection node, and we keep evaluating S2. And of course, to do the pattern match on S1 in the first place, we have to recursively call eval here to make sure we really only pattern match on an evaluated thing. And so once we have this representation, we can actually do a whole lot of optimizations on it. And in particular, one optimization I want to talk about is something we call in-place memoization. So because we want to memorize the result of the lazy evaluation, we can actually do so using the allocation of the lazy constructor itself. So you can see here that we have this append, which is the original lazy thunk, and we will return either an scons or an indirection node. And so if we look at this program down here, so let's say we have an append where we append the stream 1 to nil on top of S2. We want to be able to kind of use the memory of append itself to store the result of the lazy evaluation. So what we do to evaluate this is that when we first see the append, we of course match on S1, which is already evaluated. And so we see that we have to return an scons 1, which we write directly into the memory of the append. And then we also have to, of course, allocate another append of the remainder of the stream and S2. And so if we continue doing this, so again, we can see that we enter up in the first branch. So we rewrite this append into another scons of 2. And we create a new append allocation, which in this case maps to null. And then finally, we are in the second branch of this definition, which means that we'll actually rewrite the append of nil to an indirection node, and we'll keep evaluating S2. And so what we are doing in this example is we are always creating new allocation for the thunks, and then using that memory in place to store the evaluated results. And so I also want to contrast this a little bit to a different optimization that we call in-place reuse, which is actually quite different, because this in-place memoization happens even if there's more than one reference to the thunk, because it really implements this memoization behavior where all the references to the thunk should see the same memoized value in the end. But Coca actually has another optimization that we call in-place reuse. which also does an in-place mutation, but only if the reference count is 1. So if there's only one reference to the allocation. And so what happens then is that it can kind of generate this yellow block. So that's like some magic that the Coca compiler generates, where it can learn whether a cell is unique. And if so, it can take the memory cell of that cell and use it for another allocation. So here we will match on the stream S1, and we see if it's an S-cons. And so if it turns out that there's only one reference to it, we can use that space and use it later to allocate the S-append, the new S-append constructor in that place. Of course, if the reference count is higher, we have to do some extra work. We have to modify the reference counts a bit and allocate a new cell. So these are two very separate optimizations, but it actually turns out that you can use them together. So in this example, we can use in-place memoization to turn the S-append either to an indirection node or an S-cons. And we can use in-place reuse to dynamically see if the S-cons from the first stream, if it has a unique reference count, we can use that memory for the S-append cell. So if we look at this in this example, we have the S-append that we want to evaluate, and we'll rewrite it into an S-cons node. And if it turns out that the S-cons node from the first stream actually has a unique reference count, we will turn that one into the new S-append constructor. And then again, we apply in-place memoization to turn S-append into S-cons, and in-place reuse to turn S-cons into S-append. And finally, in-place memoization to turn S-append into an indirection node. And so the important thing about this optimization is that it means that if the first stream actually has fully unique reference counts, we can do a lazy append function with just one allocation, namely for the initial S-append lazy constructor, which ends up becoming an indirection node in the end. So we have benchmarked this, and we wanted to benchmark it in a setting where laziness provides no benefit. So we've looked at the heap and queues benchmarks or heap and queue example that Okazaki provides. And we made a benchmark where everything is evaluated, and in particular is not shared, which means that in this case, the laziness doesn't really benefit the program, but it allows us to kind of capture what the overhead of all of the allocations and so on that you need for laziness is. And so you have three systems. So this is only the first benchmark we have. So there's three systems. There's Coca, Occaml, and Haskell. And the first bar on the left is the strict version, which we use as our baseline, and the bar on the right is a lazy version. And so we can see that laziness can have a pretty high overhead if it doesn't really benefit the program. So in Coca, the overhead in this case is even 5 times, because maybe Coca laziness is not that well optimized. But even in a language like Occaml or Haskell, you can have a pretty high overhead just from the allocations. But what we see here in red is that our version with lazy constructors can be much cheaper. And in particular, for the bankers queue, that one uses the streams with the append a lot, where we can save a lot of allocation and are a lot faster because of that reason. So to conclude my talk, the key ideas from this talk are that a lazy thunk can be defunctionalized into lazy constructors. The lazy constructors, in particular, are constructors which can be printed for debugging, for example, to inspect your program. They can also be memoized in place for better performance. And all of this is implemented in the Coca language, which you can try out. And if you want to see more examples of laziness, in particular of lazy constructors, please come to my talk in the Haskell workshop, where I'll also talk about lazy constructors a little bit. Thank you.
Hi. So it seems that all the benefits are operational, and there's like this closed world assumption about the whole thing.
Yep.
So why have the user write these? Like, why not do a whole program discovery and defunctionalization behind the scenes?
Yes, so you could also do this behind the scene, but in particular, I think it is nice to make the user write it because you can get good names for your lazy constructors, right? Like, I mean, for example, you could do a whole program transformation that just comes up with some name for each constructor and then for example, if you want to print it, just prints like a string that shows you the closure. But I think it can be a bit nicer if it's actually like a first order representation.
Yeah, but I mean, it's just a huge hassle because now it's very anti-modular. You have to put all your lazy function definitions in one place. They all have to be top level. So there's like a real cost to the human complexity of it.
That is true. You have to think about it a little bit more, yes. So I mean, I've spent a lot of time looking at the data structures in Okazaki's book. And I think there it's actually very nice to use this interface. For several reasons. One is that there's not actually that many thunks. So in lots of Okazaki's data structures, there's like 2 or 3 different thunks types. And it's actually nice also when you're like thinking about your data type, not to think about, oh, this is like a tree which has like a weird closure in the middle, but to think of this actually like a constructor in your tree, so that like the constructor kind of preserves the tree shape. But yeah.
Okay, so hi, thanks for the very nice talk. I'm wondering how far you can go by just having maybe a simpler feature where you just allow constructors to have lazy fields, where you can say, oh, here's a constructor and one of its fields is lazy. Could you do a lot of what you're doing?
I'm not sure I understand how this would work.
Okay, well, the reason I'm asking is because this is probably the way I would do it in a language like Scala, where I believe you can already encode all of this in Scala, like most things. And so I wonder if you thought about this, about the object-oriented perspective on things, because this is getting quite close to the object-oriented perspective. In Scala, you can define enumerations like algebraic data types with several cases, and they can have lazy fields. So these can represent the lazy constructors that you're presenting. And you could also similarly avoid allocations.
Okay. I'm not that familiar with the Scala approach to this, so we should maybe talk about this after.
Yes, let's talk about it more
break.
offline.
Thank you.
So I'm liking this result a lot. I'll be on the lookout for use cases for it.
Yes.
Something it seems to have a similarity to, though it's definitely very different, is codata. Because you have the idea of it's a constructor-like thing, but it's got some computation attached to it.
Yes.
Do you have any insights onto, are there actual connections, or is that just a surface level thing?
No, there's certainly a connection, and we also talk about this a little bit in the related work to our paper. I mean, I think in the end, the implementation is very different, right? In the sense that, for example, codata normally don't have memorization and stuff like this. But yes, there's certainly similarities.
Hi there, very good talk, really interesting stuff. It sounds to me like the definitions of lazy constructors that you've highlighted means that every lazy function you want to write, you have to sort of define upfront when you're defining the data type. Is that true? And if so, have you thought about ways that you might allow third party, as it were, lazy functions to be defined over existing types?
Yeah, so I think there's two ways to do this. So one is, so if you at the start create this sDelay constructor, then you can kind of, you can still add new lazy definitions to it later, but of course you don't get the benefits of other lazy constructors. I mean, there's some ideas like open data types, for example, that would get you maybe some of the performance benefits as well. Yeah.
Thank you.
Yeah.
So I have a question myself. So what I didn't get is what is the impact on the semantics of the data type? So if, like with regular laziness, you would have a sort of, you would allow just infinite structures with these constructors. So here you seem to allow infinite data types as long as they keep passing over a lazy constructor or something, or?
No, so we do allow lazy data, so we do allow infinite data types as well. And so we have
arbitrary infinite trees, right?
No, we actually allow arbitrary infinite trees. So you can, for example, create a new lazy constructor that like keeps adding like one element to the stream and then...
Yes, but I mean, for one definition of a data type with lazy constructors, you don't get arbitrary infinite trees with the constructors, but your cycles are sort of restricted to follow what you define in your lazy constructors.
Yes. So I mean, if you fully evaluate the lazy constructors, you could get an infinite tree, but of course it's always suspended at some point using the computation that you've defined in the lazy constructors.
Yeah, so it seemed like an interesting sort of semantic result that you get, but I don't know if you've...
I'm not sure. I think all of this can also be modeled with regular laziness as well, but I'm happy to talk to you later.
Okay, maybe I should read the paper better.
Yes. Thank you.
Other questions? Maybe last question?
This is a very short question. Does the lazy constructor allows just the core to itself without any other extra structures? So like for example, in this case, SDLA app goes to SDLA app.
Yes.
If that kind of thing is allowed, then what happens if we match on that?
Yes, so you can define non-terminating computations in this case, and so Coca actually has an effect for divergence, and so we try to estimate whether we think your lazy computation will terminate or not, and if we think it doesn't terminate, then actually you'd get a divergence effect as well.
So it diverges when you pattern match on that?
Yes.
I see.
It can, yes.
Okay, so let's thank the speaker again. And our final distinguished paper for our final speaker for this session is Tsungju Chang from the University of Toronto, who will tell us about a new
Okay. Testing. Okay. All right. We'd like to welcome you to today's session on algorithms. Our first speaker will be Young T, and he will be giving his talk. He'll talk about what it's about. An interesting fact about him is that he's dressed like a tree today for reasons that will become clear.
All right, hello everyone. Can you hear me just right? Cool. Okay, cool. Welcome to my talk. Today I'll be talking about pushing the information theoretic limits of random access lists. This is joint work with Edward Peters and Michael Adams, who is my PhD advisor. So I would like to begin our session on algorithms with what I suppose is the functional programmer's most familiar data structure, which is the singly linked list. And it's awesome, right? It's simple to implement, it's purely functional, fully persistent, and some of the operations on singly linked lists are very performant. For example, cons, or prepending an element, is in O of 1, and obtaining the tail of the list is also in O of 1. Some other properties are, for example, you can cons two different heads onto the same tail in a singly linked list. And these are really nice. However, we know that a singly linked list, to perform a lookup or accessing a random element in the list, requires traversing up to n-1 pointers. And that is not so nice, right? Starting at that cell. And it also has a jump pointer, which points further down the list. So you can see on the slide, the jump pointers are represented by the dotted arrows. So Myers lists share most of the same properties as singly linked lists. For example, an O of 1 cons, tail, and it also supports tail sharing. But what's nice about the jump pointers is that it allows us to perform lookups in 3 log n minus 5 pointer traversals. Okay, and that's much better. However, we know that the information theoretic limit for performing lookups on linked data structures is log n, right? For example, in a binary tree, starting from the root, we can access any node in the tree in log n pointer traversals. So the question that we want to answer is, can we do better as per usual, right? So in our paper, what we have done is to kind of play a game, okay? And the game is that we want to push the lookup complexity of Myers list from 3 log n minus 5 down towards the information theoretic limit of log n. And we do this by only modifying where the jump pointer of each cell points to. Okay? So these are our contributions. Of course, we have the singly linked list, not created by us. And the first thing we did is to create or produce a new lookup complexity analysis of the original Myers list using recurrence equations. That is opposed to the original analysis done by Myers using a skew binary number system. Then we also introduced 2 new variants of the original Myers list. The first is what we call an improved Myers list with a complexity of 2 log n minus 3. And the next variant is an advanced variation of the Myers list, which has a lookup complexity of 1 plus 1 over sigma log n plus sigma plus 9. Okay, but basically, it just shows that it's possible to approach or have a lookup complexity that is arbitrarily close to the information theoretic limit of log n. Okay, and the key insight that I would like to share with all of you is that we want to view this list-like data structure as a tree, and hence why I'm dressed like a tree today. So, and what I'll show is that there's 2 key reasons why we do this. Okay, the first is that it makes it easy to analyze the lookup complexity via our favorite recurrence equations, right? The second is it also makes it easy for us to create new variants of this data structure. Okay, so I'll first start with an overview of the original Myers list, which we call the basic Myers list. So remember that each cell of a Myers list has 4 fields. And the first 3 are pretty straightforward, right? Value is the value at that cell, so on and so forth. The remaining question really is, where does the jump pointer of each cell point to? So Myers gave a very simple rule, and it's roughly as follows. Okay? Suppose we're given a cell C at the front, and we're trying to decide where that jump pointer points to. And let's suppose the next cell from C is some x's, okay? And the rule is this. If jumping from x's to some y's traverses the same distance as jumping from y's to z's, then the jump pointer of C just points to z's. That's basically it, okay? And of course, in any other case, the jump pointer of C is just the same as its next pointer. And just like this, we are able to characterize the structure of a basic Myers list. So if we use this rule to iteratively construct a basic Myers list, what we get is a list that has this kind of structure. One thing that you'll notice is that certain regions of the list has the same pointer structure, right? So for example, if we looked at this list starting at, or the region starting at F and ending at 8, it has the same structure, at least modulo renaming and all that, to the region that starts at cell 8 and ending at cell 1. Okay? Moreover, every region has 2 subregions, each of which having the same pointer structure. So my question, the question that we were asking is, well, we know that every region has 2 subregions, right? So in reality, what it means is that each region looks something like a tree, right? So let's look at this recursive construction rule and try to move things around to better reveal its tree structure, okay? So this is a region. It has a first cell L and a bunch of cells after that. What we'll do is we're going to let L, that first element, be the root of our tree. M is going to be the root of the left subtree, and N is the root of the right subtree, okay? So we're just going to move things around and we get something like that, okay? It's not really a tree and it has that P over there at the right-hand corner. It's weird, okay. Let's do the same thing on an actual list, okay? So we have this longer Myers list. Same thing, we move things around, and this kind of looks like a tree now. A little bit, right? Of course, omitting that cell number 1, we'll deal with it later, okay? But it is sort of a tree, okay? Now, remember, why do we do this? Okay, the first reason that we'll tackle is it makes it easy to analyze its lookup complexity, okay? So let's talk about that first. So, returning to a Myers list, how does a lookup or access, random access work? Okay, the idea is very simple. Suppose we're traversing from cell E to cell 2. We just take jump pointers greedily as long as we are not exceeding where we're trying to go. So from E, we jump to B, then to 8. From 8, we can't take the jump pointer since it exceeds where we're trying to go, cell 2. So we just take the next pointer, right? We do this over and over again. Eventually, we will arrive at our destination. Now let's move things and have a look at a traversal in this tree view, okay? Just side note, there's the cell F and G over there. They don't really exist. I'm just putting them there to show the complete tree structure, okay? But more importantly, by looking at a traversal in the tree view, what we see is that a traversal from a source to a destination can be split into 2 separate phases. The first is an outward phase that starts from the source and ascends up the tree, arriving to what's known as the target uncle of the source and destination, that is highlighted as cell 8 over there. From the uncle, we descend down the tree via the inward phase to our destination, okay? Now what's nice is that by splitting each traversal into 2 separate phases, we can analyze each phase individually using recurrence equations, okay? I won't go through the equations today, but at least intuitively, you can kind of see that the outward phase ascends the tree of height log n, and the inward phase descends the tree similarly of height log n. The only difference is that in the inward phase, to traverse from a cell to its right child, you need 2 pointers, right? So it sort of takes twice as long, okay? So overall, the lookup complexity of basic Myers list is 3 log n minus 5, okay? Now that's the intuitive argument. Again, for the formal proof, you can have a look at our paper, okay? So that's the first reason why we care about trees, but I guess more importantly is, excuse me, is that we would like to create new variants of a Myers list. Okay, so let's see how we can do that. Okay, so I'll talk about the improved Myers lists. And the fundamental idea is that we want to take regions of a basic Myers list and make it even more similar to a binary tree. Okay, so how can we do this? Okay, we look at the recursive construction rule of every region in the basic Myers list, and we know that a binary tree has more or less two additional properties. Okay, the first is that the subtrees of a binary tree don't share any cells. Okay, so let's do that first. Right now, both regions share this cell n over there. We don't like that. Let's split them up. Okay, we split them up into two distinct regions. And the next thing in a binary tree is that the root of a tree points to both its left and right child at the same time, right? So what we're going to do is we're just going to move the jump pointer of cell L to point to the root of the second subregion, which is Q. Okay, so I move it this way. And that's it. Okay, just with these modifications, we have arrived at a new data structure that is more close to a binary tree. Okay, and this is called, or this is what we call the improved Myers list. Okay, so if we just move things around once again, just to reveal its tree structure, you can tell this more closely resembles a tree, right? And just to show you an example of a improved Myers list, this is what it looks like, right? And if I just de-emphasize some of the pointers, you can tell, hey, we have recovered a tree-like structure. Okay, so how are our lookups perform in this list? It's pretty similar, right? You can tell that if we were to perform a lookup from cell D down to cell 2, it can still be divided into two separate phases, right? You have the outward phase from D to 8. You have this additional next pointer to the uncle. And then from the uncle, again, you can descend to the destination. Okay? More importantly, what has happened is, well, firstly, the outward phase length remains at approximately log n, okay? But more importantly, the inward phase cost was 2 log n, but because now we have direct pointers to the right child, in an improved Myers list, the inward phase length is now log n, right? So we went from 2 log n down to log n. And so the overall lookup complexity is 2 log n plus 1 minus 3, okay? So basic intuition, or the key idea, is that we, view things as trees, move things around, that gives us better performance, right? Okay, of course, 2 log n is still some ways to go from the information theoretic limit of log n. So once again, we have to ask, can we do better, right? So what I'll do is I'm just going to briefly talk about the advanced Myers list. I would say that it is a very, very complicated data structure, so I won't be going into all the details in my talk, but I'll just try to give you some intuition behind how it works, and I'll leave the rest of the details up to you to read in the paper. Okay? So first and foremost, let's just investigate the causes of slowdowns in our improved Myers list. Okay? So we have over here an example of a larger improved Myers list and a traversal from cell V to cell 2, okay? And I've highlighted the actual traversal in this data structure. Now, one thing that you notice is that, again, the traversal is split into two phases, but each phase is already at the information theoretic limit of log n, right? So you can see, zoom out to the tree again. The tree has height log n, and each phase descends the entire height of the tree. Individually, optimizing these phases is very difficult because it's already at the theoretic limit, right? So how can we optimize the lookups of this data structure? The thing that, or the approach that we took is to kind of play a balancing act, okay? The idea is we are going to modify our list data structure so that if the inward phase is long, what we'll do is to make the outward phase short. And correspondingly, if the inward phase is already short, then it's okay. The outward phase is allowed to be long. Okay? Fundamentally, it's about balancing the paths so that the overall path length is approximately log n. Okay? So, how do we go about balancing these paths? The first thing that we do is that looking at this larger tree structure, we are going to introduce skip layers, okay? The idea is this. We choose some value sigma that is at least 1, okay? In this example, sigma happens to be 2, okay? every layer of the tree starting from the bottom every sigma layers starting from the bottom is a skip layer. In these skip layers, we have skip cells. And the idea is that we are adding additional pointers to every cell in the skip layer, okay? And these are what we call uncle pointers. Now, the idea is that in a skip cell, the uncle pointer points to a right sibling of either itself or some ancestor, okay? The question is, well, which uncle does each skip cell point to, okay? To answer this question, in the paper, we assigned 2 metrics to each cell, okay? There is a notion of a right edge depth. That is the distance of a cell to the closest ancestor that is along the rightmost edge of the tree. There's also a notion of a right-handed depth, and that is basically the distance of a cell to the closest ancestor that is a left child. Now, right now it's like, okay, what is all these different metrics? For this talk, it's not too important. The main idea is that we have a fixed metric which allows us to assign uncle pointers to each skip cell. And fundamentally, the result is that the sum of the inward phase and the outward phase is about log n plus sigma, I should say. Okay? So the effect is without uncle pointers, we have this notion of double descent, where a traversal descends the height of the tree twice. With uncle pointers, we can shortcut and skip a portion of the outward phase such that the total lookup complexity is about log n plus sigma. Okay? There are some other edge cases in the paper which I will omit. Basically, what we also do is add more pointers to the leaves of our tree. Okay? I'll address one last point since I'm out of time, but basically I stated at the beginning of the talk that we are only going to modify where the jump pointers point to, right? But I added extra pointers, so technically we cheated. Okay? So to address this, what we do is instead of adding additional pointers, what we do is we don't add pointers to cells, but instead, logically, we just group some cells together so that the extra pointers are repurposed to become the pointers that we want, okay? So in reality, this isn't our data structure. It actually expands a little bit more, and therefore, the lookup complexity increases by a factor of 1 over sigma, okay? And just to give you an illustration of this structure, you have this really messy thing. It expands to something even messier, but fundamentally, there's only 2 outgoing pointers per cell.
Trees are great, so I'm now losing why you want to start from the Myers list. Why not using the tree from the beginning? So what's the benefit of using Myers list?
Okay, thank you for the question. The question, I believe, is since we love trees so much, as is totally justified, why not start from a tree? The idea is that we want to retain list-like properties. For example, being able to cons from the head or obtain a tail in O of 1 time, so on and so forth. Well, you could start from a tree and add all these properties onto binary trees. For example, an O of 1 cons, O of 1 coulter. And the resulting structure is something that is called the Okazaki list. So it's a different data structure. If I could show you what you get if we start from a binary tree, it's something like this, where you have a bunch of binary trees, and if you amend this binary tree data structure to support list-like properties, you get something like this. You get an O of 1 cons and coulter, and so on and so forth. Now, this happens to have a lookup complexity of 2 log n approximately. So we decided not to start with this. We started with Myers list instead. Yeah, thank you. Okay.
What is the amortized cost of adding a new element to the head of the list?
Thank you. Okay, what is the cost of, I guess, cons, basically? So let me quickly come here. Okay, for basic Myers list, the worst case is always O of 1. For the improved Myers list, if we are willing to maintain some additional metadata in which costs O of 1 space, the cost is O of 1 still. But for advanced Myers lists, we are actually not sure. The algorithm that we are aware of is approximately O of log n. That is, yeah, but I think that is a future work that we are willing to explore.
Thank you.
Thank you.
Right. One quick question about the memory usage that clearly goes up. I'm guessing it's still a linear blow up. But how? Like, what's the constant? How much extra space does this take compared to a regular const list?
Oh, twice.
Oh, exactly twice.
Yeah, because the cell structure is, well, each cell, instead of having 2 fields, it has 4. And that's it.
Right, but you add extra nodes as well, right?
Oh, no, we don't. We don't, yeah. So, okay. So I guess you're referring to this part where we cheated.
Sure.
Yeah, so, okay, so I alluded...
No, it's the one with extra layers, the tree with extra layers. You have that.
Okay. So the idea is not necessarily that we are adding extra data over here. It's more of the fact that if I could use my laser pointer, is that this happens to be the first cell, and then second cell, third cell, and so on. It's just moving the cells around.
Okay.
But it's the same space. Yeah, thank you.
I'm interested in the constant factors. You wouldn't, for example, have an extra slide with some benchmark results on, would you?
Oh, okay. That's a very, very good point. Okay, we didn't do runtime benchmarks. In our paper, we have theoretical benchmarks, if there's any consolation. But, well, these are the theoretical benchmarks. We just wanted to do a sanity check on how the performance or comparing the real-world path lengths to the theoretical ones. I would say that the advanced Myers list has a much larger runtime overhead, primarily because the cost of computing what the path actually is takes a little bit long. So for us, our goal is kind of to just forcefully reduce the number of pointer traversals, which could be useful in any scenario where pointer traversals are very expensive. For example, if a pointer traversal corresponds to a network lookup, right? But yeah, it's a little bit slow for advanced Myers list, I would say. Thank you.
Oh, so are you actually planning to do any real-world testing, or like seeing actually how it performs in practice?
Oh, okay. We have done some real-world benchmarks. We didn't really optimize our implementation for finding the paths in the list, but there is a overhead for using advanced Myers list. The improved Myers list is okay, so it still roughly corresponds to the theoretical result. Yeah.
Thanks.
Thank you.
Okay, let's thank Young-Si once again.
Thank you.
Perfect. Our next speaker is Alexander, and Alexander's favorite programming language right now is Haskell. Or no, it's Agda. Agda, sorry.
Yeah, for this we use Haskell as our implementation language. So in this talk we are going to look at functional solutions for the longest uptrend problem. And before understanding the solutions, we have, of course, to know the problem. For those who don't know the longest uptrend problem, or better known as the longest increasing subsequence problem, here's a brief description. So given a sequence of elements, we are looking for the longest subsequence that is strictly increasing, and the subsequence is given by just removing 0 or more elements from the original data. Here you can see an example. In orange are, the orange dots are the longest increasing subsequence. Actually, in general, we have to talk about a longest increasing subsequence. It's not unique in general. So this problem is a very standard problem, and we tried to come up with our own functional. So in the imperative world, it's a standard problem for program derivation, and we wanted our own implementation functionally, and we implemented it, and then we made something that one shouldn't do if one wants to avoid problems. We implemented also the imperative solution and benchmarked them against each other, and of course the imperative solution was much faster, so roughly 6 times. And so the goal for us was then to come up with a solution that is on par in real world with the imperative one, because we believe that functional programming is at least as good as imperative one, also performance-wise. So, and to understand what was our mistake first, let's have a look at the imperative standard solution. So here you can see some pseudocode, and you don't have to understand all the details. The main idea is that we have an array. Here it's called S. And in the array S, we store all the, in the array S, we store at index I the longest increasing, at the index I, we store an up sequence that has length n minus I. So you see at the end, we return Sm, and the length is n minus m. And the main logic happens inside this for loop, where we go over all elements in reverse order. And what we basically want is to extend an up sequence that we are given. So in case we can extend the longest found up sequence so far, yeah, we do this. And otherwise, we perform a binary search to find the smallest I, such that the sequence at position I is extensible. So we have here Si, that's extensible by A, and we extend it and replace Si minus 1 by the new extended sequence. So Si minus 1, the head element is smaller than A by definition. So this one has the same length, but is better because its head element is greater. So, and now what we did was to basically take this implementation and translate it directly into functional code, by basically just replacing the array with a persistent sequence type. And if you do this and choose the correct sequence type, you still get the same asymptotic performance. You see here in the for loop, the only non-constant time operation is the binary search operation. And this takes log n time, so the whole solution takes worst case n log n time. And so, and if our solution, if this sequence type supports binary search, lookup, and update in log n time, we still get a functional n log n time solution. But you see in the benchmarks, the performance is in reality much slower. So, and our mistake was that exactly this part here, that we used integer indices to communicate. So we use integer indices to perform the search. We make a lookup, and we move also in the sequence. So here you see we have I and I minus 1. So we use integer indices for all different parts, and that's quite slow in a random access list in our case. So now we take a standard solution. We take with zippers instead, and yeah, instead of using integer indices, we are going to use zippers for encoding our positions, and then we have, of course, to adapt binary search to work with zippers, and in the end, we adapt the longest uptrend implementation to work with the new binary search. So here's a quick refresher on zippers. So zippers are, as I said, functional solution for encoding locations. For example, here we focus on the location on the node 4, so we have that's our focus, and a zipper consists of a focus and of a context. In the first case, the context is empty, indicated by the T, and we can move inside the data structure. And since, I forgot to say, we are first using zippers on binary trees, and because that's what we are going to use. So, and we can go right or left, and then right and then left, and then we have here our focus is on the tree with root node 7. So we can have direct access to the 7, and the remaining part here is the context. So, and the context is basically a tree with a hole and an upwards pointer. And so, and a location is then just a pair. So how does binary search now look like if we use zippers instead of integer indices? And so the input to binary search is really still the same. We take a predicate and the tree, but instead of returning an index, we return a zipper, but not one, but 2 locations. Why this? So we return a tipping point, and if you want to know why it's in general the right thing to do to return a pair in binary search, you can attend my talk on Wednesday where I am going to talk about binary search in general. But here we can also already see why it's a good thing. You know, here, as I said, we use the position I and I minus 1 to perform a lookup and an update. So actually we, using integers, obfuscated the fact that we move inside the tree. So actually we have 2 locations, not 1, and binary search returns both locations, a tipping point, and now the binary search is implemented by a worker function, find. And let's have a look at an example where we, where our predicate is if 5 extends the sequence. So in our tree, we store up sequences. And since we are only interested in extending them, only the heads are visible. So you can think of P if 5 is less than the element given. So we are focusing on the 4 at the root. And now 5, of course, does not extend 4. So we have in our operation find, we have the current location where we are looking at. And we have also 2 accumulating arguments. And since 5 does not, so for the potential left endpoint and potential right endpoint, and I forgot to mention why we are returning maybes, because the tipping point could be on the very far left or on the very far right. So we are using maybes for this. So 5 does not extend the sequence starting with 4, so we have a potential left endpoint, the negative point of the negative part of the positive part. So that's then our tipping point as expected. So how does this help now with the longest uptrend problem? So now the longest uptrend function, it starts as in the imperative solution, it starts with a singleton tree in this case containing the empty uptrend. That's always a solution, that's always an uptrend, and in the end we return the leftmost uptrend in the tree, so that's then the largest one. And now the main logic happens inside the insert operation in fold R. So we have 2 cases. First, we first we look at the second case here, the second line. So in this case, we have 2 locations given, and now we have direct access to the uptrend starting with 6 in our example, and the uptrend starting with 4, and we are doing and we are doing the replacement. So we take the uptrend starting with 6, add 5 in front, and put it in here, and replace it, and zip the left endpoint, so we make a tree out of it again. So that's the one case. The other case is if the tipping point is on the very far left. It can't be on the very far right because the empty up sequence is always extensible. So it can be, but it can be on the very far left. What are we doing in this case? In this case, we take the we are then at the leftmost element, and we, for example, if our element that is our A is 0, we just take the uptrend, extend it by 0, and make it the left child. So far, so good. But unfortunately, this picture is a complete lie, because we get into this situation, as you probably already noticed. The only part where we are extending the tree is in this second part I showed you, and it's always extending to the left. So actually what we have is a degenerate tree, and binary search is just another name for linear search. So that's not fast at all, and we get actually an n-squared algorithm. And again, fortunately, there is an off-the-shelf solution for this as well. We take Okazaki's red-black trees, and it's actually quite easy to adapt to red-black trees. So everything just stays the same. We have to add color fields to everything, and instead of zipping, we have to balance as well. So let's have a look at an example. So you can see here our input sequence, and we start, of course, with the singleton empty uptrend. So 8, of course, extends the empty uptrend, so we make it the left child, and when inserting something, we color it in red. So now 9 does not extend the uptrend starting with 8, but it extends it with the empty uptrend. So the tipping point is here in between. So instead, 9 now will replace the 8 here. So now 6 extends 9. So 6 becomes the leftmost child, and since we are having a red-black tree, we make this rebalancing operation. So again, 7. For 7, the tipping point is in between here. So we replace now the 6, the uptrend starting with 6, with the one starting with 7 that extends the one here. Now 4 again extends 7, 5 updates, 2 extends, and we have to rebalance again. Now 3 again, here is the tipping point. 0 extends, 1 replaces, and 0 in the end extends again. And so 0 extends again, and we make 2 rebalancing operations, and the tree is nicely balanced. So if you watched closely, you noticed that actually we only operated on the left spine. From the rebalancing operations I showed you earlier from the red-black trees, we only used 1, since we're operating on the left spine. So this leads us to the idea that maybe instead of using red-black trees, we use the left spine view of the red-black trees, and indeed, if we watch closely, we see that actually, if we are the shape of the red-black trees are very regular, and we are working on a numerical representation with digits 1 and 2. So if we have a black node, that's 1. So, but if we have a red node, then there must be a black node with the same height again, and here and here, and for example here and this one. So, and this is then a 2. So now instead of using red-black trees, we can actually just operate on the left spine view instead. And we actually don't need red and black nodes anymore, because we can just encode the digits inside the data structure, so as a data type. And so again, we have to we perform the same things as before. We have again to define zippers on the left spine view, and interestingly, the left spine view is already itself a zipper. Yeah, it's actually the zipper of the leftmost leaf. So, and so if we now define zippers for the left spine view, we actually have zippers of a zipper of a zipper. And yeah, again, we have then to adapt binary search, and this becomes now exponential search, because we start at the very left, yeah, and the trees are growing. So, and yeah, and in the end we replace just the binary trees with a red-black. We replace the red-black trees by the left spine view by these finger trees. And if you want to know the details, you have to look into the paper, in particular also the correspondence between exponential search and this search in the left spine view. And so our initial problem was we wanted to have a real-world fast implementation. So did we succeed? Here are some benchmark numbers, so the same benchmark again, but now with some other implementations. So the black line here, this was the imperative solution, and this one was our initial failed attempt. Here's another standard solution from algorithm design with Haskell from Bird. And so you probably, it's fairly visible. So in dotted black, you see the imperative solution by using exponential search instead. And then in blue, you see the solution using red-black trees, and in green, the left spine view implementation. And they are all fairly close. Why are we using then, why was it worth to implement the finger trees as well? So if you remember back this example here, we only extended to the left, or the tipping point was here between the leftmost element and its neighbor. So in this case, and so if the input sequence is nearly sorted, then we only operate farther to the left. And in this case, we have adaptive behavior, and it's much, much faster, and we get actually linear running time instead. So if you want to see more benchmarks, also I also refer to the paper. So for the conclusion, it's obvious actually for us, I think, don't translate imperative code directly into functional one, but we have unfortunately fallen into this trap. And in particular, this means don't use indices blindly. Use instead zippers, use contexts. indices are fine for array access, but they are probably not fine for accessing functional data structure. Yeah, and it was at least new to us that finger trees reify exponential search as binary trees reify binary search. Thank you.
Thanks for the talk. One question I have about how to use zippers in practice for that. So if I have multiple indices, I can use them one after another to edit multiple things in my data structure. How can I do that with zippers? Because the standard way I see it, you can only have one zipper at a time.
Yeah, that's true. So in maybe I should have added to the conclusion that you have to really know the problem at hand, because in our case it was really possible. But if you want contiguous indices, then I don't see how it works. Yeah.
Oh, just you also had your binary search returns two zippers. How does it work there?
So
like it returns two locations.
Yeah, I showed it in the example. So we have this left argument and the right argument, and you remember this example. Mm-hmm. So we have, and we just have as our accumulators two zippers, and of course they share data, but yeah.
Hello? Okay, this is better. Right, so yeah, it's good that I'm talking behind the two previous talks, because this talk will be about subsequences and also will be about trees. So anyway, our task today is to compute this function h, which takes a list as its input, with the property that h of x's is defined in terms of the values of h on all the immediate sublists or subsequences of x's. And by an immediate sublist, I mean that a list of y's is an immediate sublist of x's if y's can be obtained from x's by removing exactly one element. Okay, so for example, to compute h of ABCD, we need the values of h of ABC, ABD, ACD, and BCD. And to compute the value of h of ABD, for example, we need the value of h of AB, AD, and BD, and so on. And if we compute in this top-down manner, you will see that we end up doing lots of recomputations. Like in this picture, h of AB is computed twice, h of AC is computed twice, and when the list gets longer, we will see more repetitions. So it will be preferable to have some bottom-up strategy, which computes the value of h level by level. So probably in the first level, we compute the value of h for all the sublists of length 1. And in level 2, we compute the list of h for all the sublists of level 2, and we keep going up like this until we reach the top. And so as a visual aid in this picture, dependency from the same value are drawn using the same color, but it's not essential to understand this talk. And so then you might imagine implementing this algorithm by representing each level as an array, and then to compute any particular value, you use some smart in bit level index computation to find out where the values needed are in the previous level. But however, this bit level computation is not going to be as easy as it seems, and your code will not be pretty. I'm sure you're not going to like it. So instead, we are going to develop some data structure for this purpose today. And this algorithm, this problem was actually started by Richard Bird in one of his 2008 paper, and the purpose of that paper was to study the relationship between top-down and bottom-up algorithms. And this problem, Richard used to say that 3 examples make a paper. And this example was the last one in his paper. So in the algorithm, at the core of the algorithm he presented is a short function divided in 4 lines, which I couldn't understand at all. And it's very concise, looks pretty, but I couldn't even say clearly what this function does at all. And so and being the last example, Richard didn't want to spend too many pages on it. See, he simply presented it and claimed it correct. So I was looking at the algorithm and thinking, is it possible for me to understand this function or even to calculate it? And that's the motivation of this piece of work. Okay, probably time to get to be a little bit more formal. So this function subs takes a list and computes all the immediate sublists. The definition is standard. There's no immediate sublist for an empty list, and the immediate sublist for xcons axis is either axis or the sublist of x's with x attached to the left. Okay, so then our top-down function as a specification, our top-down function can be specified by 2 functions f and g. So for the sake of presentation, we are going to consider only non-empty lists in this talk and in the paper. So the base cases are singleton lists, and for which we apply the base case. In the base case, we use the function f to get the value we want. And for lists having at least 2 elements, we compute all these immediate sublists, apply edge to all these sublists before collecting all the results using a function g, having type list of y to y. Okay, that should be very clear. And then what about the bottom-up computation? So how do we build one level from the previous level? The computation from one level to the next can probably be seen as a 2-step process. So in this slide below is level 2, and above there is level 3. So you see, for example, to compute h of ABD, we need the values of h of AB, AD, and BD. And to compute h of ACD, we need the values of h of AC, AD, and CD. So if we can somehow construct a metric function, which I'm going to go upgrade, which takes level 2 and copies and regroups the value such that all the needed value are grouped together, then we just need to do a map of G to compute level 3. And now I'm going to call this middle level level 2.5. So if we can construct this function upgrade, which has type list of B to list of B, and the bottom-up algorithm would look like this, that we start with having a list of x's. We start with doing a map F to compute level 1. And then we do map G after upgrade n minus 1 times, where n is the length of the list. And by the time you finish, there should be, at the top, there should be just a singleton list whose value you can extract. Okay, right. So now the problem is to construct this function upgrade. But what does it do anyway? We had to build the function, we need to have a clear specification. So can we write down formally what it does? To do that, to talk about what it does, we need to talk about this function choose, which takes a natural number k and a list called axis and gives you all the way to choose k elements from the list axis. And the definition is also standard. So there's one way to choose 0 elements from a list, which is the empty list, and to choose 1 plus k elements from xcons axis. For example, we can either keep x and choose k elements from axis, or we can drop x and choose 1 plus k elements from axis. And this function choose returns a list of A, so the results of these two recursive calls are just appended together. That's choose, which is also standard. Okay, now that we have choose, we realize that the level 2 is actually the result of map edge after choose 2, and level 3 is actually the result of map edge after choose 3. And what about the level 2.5? If we can say clearly what it is, then we have a specification for upgrade. But what is it? Right. Upgrade should be a natural transformation. So if we just forget about edge, then this level 2.5, what is level 2.5? So ABACBD is actually the sublist of ABC. ABADBD is actually the immediate sublist of ABD. So actually, we get level 2.5 from level 3 by doing a map subs. And here we have our specification. This is what upgrade does, basically. So upgrade is a function take from a list of B, list of anything, list of B to a list of B. And when it's given level k, it returns the list of B, which should look like applying map of subs to level 1 plus k. And there's some other side conditions on k and the length of axis which we can ignore for this talk. And presumably now we have a specification for upgrade. We should be able to calculate it by what? Okay, by induction, basically. Or the function choose have 3 cases, so you should be able to expand the 3 cases and do some transformation. Try to find out what upgrade should be to allow you to go from the left-hand side of the equality to the right-hand side. Then you should be able to construct this function upgrade. If you do that this way, you are going to fail at one point, because at one point you are going to realize that representing the level, each level in lists as lists, drops too much information. You need some other data structure which kind of remembers how the choices were made in choose to allow you to proceed. So instead of lists, we use some kind of tree. And this type B of A is just a tip-valued binary tree. It's a binary tree having values on the tip only. So B of A is either a tip, T of A, having a value A, or a node having 2 subtrees. And the tree version of choose, which I'm going to call C edge, looks almost like the previous function choose, with one difference that it returns a B of list of A rather than a list of A. And in the last case, rather than doing an append here, you keep the two branches, keep the 2 results of your recursive call in the 2 branches of the binary tree to remember where it comes from. So I'm going to show you some, okay, and also once we introduce the tree, we naturally have a function map for it, and another function zip bwidth, which zips 2 trees having the same shape together using a function A to B to C. Right, which we're going to use later. Okay, so I'm going to show you some examples. So later on the slides, a tip is just going to be drawn as by its value, and a node having two subtrees are going to be drawn like that. The right subtree, the left subtree will be at the bottom. The right subtree will be drawn on the right. Right. Okay. Yes. So this is what happens when we apply, when we do choose one of ABCD. It's just like a list, and this is our level 2, which we can compute by choose 2 of ABCDE. Then you can see that in the left subtree are all the choices having A, and in the right subtree are all the choices not having A. And again, in the right subtree of the left subtree are all the choices having B, and then this tree are all the choices not having B. And this is level 3. And another thing you will notice is that this subtree, these two subtrees have the same shape. Why is that? Yes, of course, because we compute the tree on the top was computed from by attaching an A to every node of this tree. So of course they have the same shape. And so basically, the tree follows a certain structure. It's not just any binary tree. So you might be thinking using dependent type to put more constraint on the shape of the tree to make things clearer, which is a good idea, but that will be a separate paper. Okay, so right, and then actually, if you compute these sizes of all these, if you compute the size of every subtree in the tree, you see this sequence of number. So in here you have from right to left, you have 1, 2, 3, 4. You have 1, 3, 6, 10. Here you have 1, 4, 10. Does that look familiar to you in any way? This is, sorry? Yes, this is actually the diagonals of Pascal triangle, which is, the first time I saw it, I was surprised, but actually now that looking back at it, it's not as surprising because Pascal triangle is very closely related to choose anyway. So, okay, anyway, back to our problem. So now the new specification of the function up is something like this, that each levels are now presented as trees. So up takes level k and produce a tree of lists, which should look like applying map B of subs to level 1 plus k. And now you can calculate up. It's a pity that I cannot show you the calculation due to time constraints, but it's probably for the best because it's more fun if you try it yourself. And I do invite you to try it, and if you are interested, take a look at the calculation in my paper. You know, the point of writing a functional Perl is that I find something fun, so I want to share with people, and so let's try this together. But anyway, now, so for now, I'm going to just show you the result of the calculation, which is this 4-line function. That's the function in Richard's paper that I saw, which confused me. And still, it doesn't it still looks mysterious. But however, now we have a specification and a calculation toward this function. So to show you how it worked, okay, now there are 4 cases. To show you how this function works, let's see an example. So now at the bottom, this is level 2. And this orange dot is where we are at. So we start from the root, and it matches the last branch of the function. So we will go all the way to the right until we reach this tree. And what is matched are the first 2 cases. The 2 middle cases, the first 2 cases of the function. And I'm going to skip the details and just tell you that for given this tree, all the 3 nodes collapse into 1 node, which gives the result is 1 node having 3 things, CD, CE, and DE. And then we go back a bit, and now that to the parent, and then go down to no here. Then we go back a bit and to this subtree. Right. So now what's matched is the third case. The third case. This one. And so now this is Y, this is U. And what should we do? It says that we should do, okay, this node is the result of up of U, which is collapsing to one node, BD, BE. Then you get this subtree by taking U and attach BC to both of them. That's why you get BC, BD, BC, BE. Okay, right. And we do one more step. So yeah, this is what happened when you apply that tree to when you apply up to that tree. And now when we are considering here, now it's the last branch, it's the last case being matched, and the two trees T and U are drawn are drawing this in the dotted square. So what we should do now is, according to the definition, is to compute up of T and then zip this with U. And why can we do that? Because they have the same shape. So then after zipping this tree with this tree, we get the tree there having BC, BD, CD, BC, BE, CE, BD, B, and BD, BE, DE, and so on. And then now finally back here, we do this. You do the same thing again, zipping that tree whose construction I'm omitting with that tree U, and that gives you the a tree containing subsequences, immediate sequences of ABC, ABD, ABE, and so on. So that's basically how the algorithm works, and that's it. So then that's how you construct level 3. Okay. Then I'm going to stop here. Thank you. Please.
I was wondering what's H? We have a mark I don't think so.
Thank you, sorry.
Yes. You can go first.
I was just wondering what H's, what are some H's that we might care about?
Actually, it's been hard to find useful examples. So I asked some friend of mine doing, because probably the question can be rephrased as what's the use of application for this. And I asked some of my friends doing algorithms, then they say that in their circles, he said, it's a common pattern they see often, and actually many problems on sequences, for example, some form of minimum editing distance problem can be rephrased into problems of this shape. And he explained that to me, and I believed him. Then now I forgot. So, however, for me, it's just a fun exercise. Thank you.
Yeah, thank you for your talk. So I hope I understood this correctly, but I think when you're going from level 2 to level 3, you have like this whole subtree that starts with the A's that you're no longer using, right? Because there's nothing you can put on front of it.
Sorry, the A's I'm not using.
So I think you are.
So, yeah. Yes, so this is the last step of constructing level 2 from level 3, and then so this tree T is transformed into this, having ABAC, ABAD, and so on, and then it has the same shape of this as this tree, so they can zip together to form this. And indeed, every values are still there.
Okay. Yeah, thank you.
Thank you.
So my question is something along the lines of, if the order of the immediate sublists doesn't matter, is there any extra performance juice you can squeeze out of it? Because it seems that some effort goes into maintaining everything the same order as you would get with the naive top-down thing.
So you're asking, if the order of things in the sublist doesn't matter, could there be a quicker algorithm for this? I don't know, actually. However, we are maintaining the shape there is mainly to allow us to do this transformation, to put everything in the right place. And now for me, the elements being in the right order seems to be a side effect. And yeah, but that's a good question. Thank you. Okay.
Thank you for your questions, and thanks you for your talk. Let's thank Xin-Cheng again.
Thank you.
Our final talk is by Brent Yorgi, and it is remote, and so we will see it on the screen. While that's being set up, this is a reminder that there is a Discord channel for papers, and you can submit questions for each paper. And so maybe take a look at that and for Brent's talk.
Hi, Bernd, can you hear us?
Yes, I can. Can you hear me?
Yeah, great, go ahead.
Sorry, what was that?
You can go ahead.
Oh, go ahead and give my talk? Okay. Okay. Will I be able to see anyone in the room where I'm giving the talk, or I should just go ahead?
No, you won't be seeing anyone. You should be able to hear the questions at the end.
Okay. Okay. Great. Thanks.
Thank you.
Alrighty. All right. Well, let me get started. So I want to start with some motivation of what we're doing. So let's imagine that you have a sequence of values, and we want to be able to do two operations. One is we want to be able to update any value to a new value. And the other operation we want to be able to do is a range query, where we want to be able to get the sum of an arbitrary contiguous subsequence of values. And so the question is how to be able to do arbitrary interleavings of these two operations in an efficient way. And so one thing we could do is just store the sequence in a mutable array. And of course, updates are very fast, but doing a range query, you just have to brute force add everything up. And another thing we could do, if you try to be a little more clever, and we could say, well, why don't we cache prefix sums. So if pi is the sum of all the values up to ai, right, then we can do a range query by just subtracting the sum of everything up through j, and then subtracting the sum of all the things up to I minus 1. And that means that range query is now very fast because it's just 2 constant time lookups, but update is slow because now to update something you have to update all of the cached prefix sums, all of it. Okay, so there are 2 nice solutions to this problem that give us log time updates and range queries. And segment trees are very easy to understand, and Fenwick trees are extremely fast but harder to understand. And so I want to tell you about segment trees first and then explain how we can understand Fenwick trees as sort of an optimization of segment trees, which is not how they're usually presented. All right, so what is a segment tree? So on the bottom here we have our sequence of values, and we just build a full binary tree on top of it where each node stores the sum of the nodes below it. Okay, and so of course the root is the sum of the entire thing, and so on. So to do an update, we only have to update the cached sums on the path from the node we updated to the root, and so that takes log time. To do range queries, well, if we focus on doing prefix queries of the range that we want, and we can add up, we don't have to recurse all the way down to the leaves, right? We can add up these cached nodes as we go, and so that takes log time as well. And then, of course, if we can do a prefix query, we can do an arbitrary range query by subtracting. Okay, so this is very nice. For this was doing like arithmetic coding, where you're keeping track of frequencies of symbols that you've seen, and you need to be able to quickly query and see, sort of cumulative frequencies for things. And apparently, also there was a paper published in 1989 which had the same idea by Boris Ryabko. But I don't read Russian, so I don't know actually what's in that paper. So let me show you, this is a typical imperative implementation of Fenwick trees. And I do not expect you to understand this code, and that is the point. I do want to point out a few things about it, though. So you can tell that whatever this is doing, it looks like it's going to be pretty fast. We're just storing an array. We're not storing tree nodes with pointers and such. You can see that there's this range operation down near the bottom that subtracts prefix things. That looks familiar. But then the prefix function and the update function are both, they have these little loops which involve adding or subtracting something called LSB. And LSB is defined as the bitwise AND of I with negative I. And so what the heck is that doing? And what does this have to do with range sums and all that stuff? So the goal for the rest of this is just to kind of explain where this comes from. This is an ahistorical, I don't think Peter Fenwick came up with it in this way, but it's one way we can understand these. Okay, so let's think about segment trees again. So back to a full binary tree with these cached sums, and it turns out that we actually don't need a bunch of these values. And so if we just grayed out some of the values, so in particular every node that is a right child, I have grayed out. And we don't need those. So you can convince yourself that it would be possible to reconstruct the values in all the grayed out nodes. So for example, the little square all the way in the bottom left underneath the 4, since 4 has to be the sum of 0 and whatever's in that gray square, right? We know that there has to be a 4 there, and so on. And you could fill in all the rest if you wanted. But we don't need to reconstruct those grayed out values. We can just do updates and range prefix queries using the existing values. So updates are easy. You just ignore the grayed out nodes. You don't need to update them. And prefix queries, it turns out we're only using the non-grayed out nodes anyway. I won't prove that for you right now, but you can convince yourself that the nodes that actually, whose values get used are the ones that still exist. And so, looking at this, it then occurs that since every right child is grayed out, we can sort of imagine every node sliding all the way down into the right until it lands in that array. And then we can actually store all the values in this tree in this array. So it's an array that's the same size as our original sequence, only every other value is actually an original value from our sequence, and the other ones are sort of these cached sums. And this is exactly what is called a Fenwick tree. And you usually see it, if you look up explanations of it online, you'll usually see it presented like this, drawn as a tree, but sort of in a right-leaning style, so that each node is kind of exists above the place in the array where it's actually stored. Update the 7, which is the parent of the 6, right? And then the parent of 7 is 22, and that's stored, somewhere else in the array. How do we know where different things are stored relative to each other? So that's the big question. So, okay, to answer this, let's go back to thinking about full binary trees. So there's a really nice way to number full binary trees that you've probably seen before. You can put 1 at the root, and just keep numbering them consecutively. Right, and this has the nice property that each the children of a node are numbered twice its value and twice plus 1. So, the 2 has children 4 and 5, so that's twice 2 is 4, and twice 2 plus 1 is 5, and so on. This has the property that every right child is odd, except the root is a weird special case because it's odd, but it's not a right child. And so we're just going to switch to using 2 for the root. Now this means the numbers are no longer consecutive, like 3 is missing, 6 and 7 are missing, but we don't really care about that. It still has this nice property that every node, its children are twice it and twice plus 1, and all the nodes on a particular level are just numbered consecutively, like 8, 9, 10, 11, and so on. Okay, so, and of course in binary this looks really nice, because to move down from a root, you just, or from any node, you either add a 0 or a 1 to the end of the binary representation, and to move up from a node to its parent, you just do a right bit shift. So that's so the point is, moving around in a tree numbered like this is very easy, right? We know to move up, we just do right bit shifts. Move down, we shift in bits, and so on. So here's the plan. If we can figure out how to convert between this numbering scheme that I just showed with a full binary tree and the indices in a Fenwick tree array, then we can move around a Fenwick tree by saying, well, let's first convert to a full binary tree index, do whatever moving around we want in the tree, and then convert back. And then hopefully we can fuse these operations together to get some kind of nice way to directly compute moving around in the Fenwick tree. So in order to do that, we want some kind of domain-specific language for manipulating numbers in binary. So this is using Haskell notation. It's not really specific to Haskell, but we can make a data type for bits. We can have not, and, or standard kind of things. And then we're going to represent binary numbers using 2's complement, which probably many of you are familiar with, but the basic idea is, so here we're counting down in binary, 5, 4, 3, 2, 1, 0, and if we imagine what would happen if you kept going, if you imagine the bits as like an odometer, if you keep counting down past 0, it kind of all rolls over to 1, all rolls over to 1s, and so we're going to use this infinite stream of 1 to represent -1, and you could keep counting down, right? You would get infinite stream of 1s and then 0, that's -2, and so on. So we want to represent such infinite streams of bits, and in Haskell, we could use an infinite lazy list, except this is really not a good idea. So we don't have decidable equality for these things. We can't convert from an infinite list of bits to a number, because you never know when to stop. There could always be more bits that you need to look at. And it allows junk values, like, something that alternates infinitely between 0 and 1 is not a valid 2's complement number, but that would be a valid list, so we don't want that. So instead we're going to use representation where we have an explicit constructor to represent infinite repetition. So basically every number has to eventually end with all zeros or all ones. And so we'll have a constructor for that, and then a SNOC constructor. I'm hiding some details here under the rug, and you can see the paper for the actual details of how this works. And then we can encode some kind of standard operations on bits, like and, increment, invert. Negation in 2's complement is just you invert all the bits and then you increment. And if you have never seen that, you can work that out for yourself. It's cute how that works. But so we saw this LSB thing in the Java code that I showed you, and LSB stands for least significant bit. And so the idea is, well, if you see a 1 bit at the end of a number, then we just say, well, the number with the least significant bit is that 1, and so we'll just return all zeros and a 1. If we have a number that ends with a 0, we just kind of keep looking recursively for where that last bit happens. And we just have a case for all zeros, just so it's total. And right, and so we saw in the Java code there was this LSB function that did a bitwise AND of I and negative I. And it turns out that we now have enough in our little DSL to prove that indeed LSB of x is equal to the bitwise AND of x with its negation. And this is an easy proof by induction. There's some other things in the DSL, like setting and clearing bits, testing bits, left and right shifts, and then this sort of generic while combinator that just keeps applying a function as long as a predicate is true. And there's various lemmas about how these things interact. We can rewrite them in various ways. Okay, so how do we convert between indices in a Fenwick array and indices in a full binary tree? So I'm going to go through this pretty quickly. There, you can look in the paper for more details, but so here's sort of, on the top, the blue numbers are Fenwick array indices, just numbered 1 through 8, and then the other numbers underneath are the corresponding full binary tree indices. If we go one more level, we can see that these numbers we had here, 16, 8, 18, 4, 20, they show up, these green numbers are the same. They're interleaved with some other ones. And we can kind of see why that happens, because we keep the same structure of the tree. When we add one more level, we sort of end up interleaving these new even values with the values that already existed. And so we can write a sort of interleaving operation on lists, and then define the sequence of values that we want inductively, right? So we start out with the base case of just 2, and then we interleave these consecutive even values starting at some power of 2 with the values from the previous layer. And so we end up with this conversion function that says, well, if you have an index in a Fenwick array and you want to convert it to an index in the binary tree, depends on whether k is even or odd, right? You either get something from the previous layer, so we have this recursive call, or right, something from this last layer looks like this power of 2 plus something depending on k. And if we stare at this and we say, well, what is this doing? So it's as long as k is even, we're going to keep dividing it by 2. That is doing a right bit shift. And if k is odd, we're going to add this big power of 2 and decrement. So we can actually encode this in our little DSL for bit strings by saying, well, we're gonna set that 2 to the n plus 1. We're gonna set that bit. We'll set it first, and it'll kind of come along for the ride while we do some shifts. And then as long as the number is even, we shift right. And then finally, once we hit an odd number, we'll do that final decrement. And you can similarly derive the inverse operation to convert back. And then if you think about what do we have to do an update, the idea is, right, we want to find the closest parent that is still active, that is not grayed out. And the way we do that is, well, you would move up one level to get to the immediate parent, but then that might be grayed out, so you just have to keep moving up until you reach something that is not grayed out. And so to move up one level, we do a right shift, and then you keep moving up as long as you are at an odd node, that is, as long as you're at an inactive grayed out node. And then we just sandwich between, convert from Fenwick to binary and do this and then convert back, right? So this is the function that would tell us how to move in a Fenwick tree from a node to its nearest parent that is not grayed out. And we could do a whole bunch of inlining things and rewriting using various lemmas and stuff. And we end up with something that looks like this. It basically says, well, you first set this pretty large bit, then you right shift, you shift out zeros, and then as soon as you're a 1 in the final place, you increment, and then you shift left again until that 1 that you set was back in the same place, and then you unset it. And essentially what this is doing, right, it's finding the smallest, it's finding the rightmost 1 and incrementing at that place. And this sort of sentinel bit is just sort of set to make sure that we can move things back to where they were before. And so you can prove, and there's a proof of this in the paper, that indeed this actually does correspond to taking a number and adding its least significant bit. And which is exactly what we saw in that Java code, right? It was saying we'll start at some index I, and then each iteration we're going to add its least significant bit to itself, and that will get us up to the next parent we need to update, and then we just keep doing that all the way up to the root. So there's more stuff in the paper. There's there's more pictures. There's actually proofs of all these things. I also talk about deriving this prefix operation, which was the thing that involved subtracting the least significant bit instead of adding. Thank you very much.
Okay, Brent, can you hear me?
Okay, Brent, can you hear me? Yes, I can.
Okay, I don't know if you were able to see the talks earlier in the session, but there's definitely been a theme of taking data structures and algorithms that were developed in the imperative world, bringing them into the functional. And one of the takeaways from a previous talk was, don't use indices, use cursors or zippers or something. I forget the exact word. But I'm wondering if you can imagine a version of what you're doing, because you've leaned really heavily into this, bits and twos complement. Is there a version that sort of makes the structure of the tree play a more central role in it and is able to move away from bits?
Yeah, that's a really interesting question. I mean, my original goal was certainly there's this existing imperative code that does this bit manipulation, and I wanted to explain where that comes from. Now, but could you make a version of it that maybe does sort of a similar things but works in a more nicely functional way? Yeah, very possibly. I'll have to think more about that.
Great. We've got another question.
Hey everyone, this is Simon. Simon PJ. So often with these algorithm things, once you pick the particular API you want, and then you can say, well, in the literature, there's somebody's done this particular piece of work that for that API you can get this data structure, and then you can, as it were, rationally reconstruct it as you've done. But that doesn't feel very systematic somehow. It's a bit like sort of points in space. If you were to add, I don't know, concatenation to these trees or range deletion or something, then would it mean we tear everything up and start again? Or could you imagine, I don't know, just having a more systematic way to construct these kind of data structures, in the systematic way that you described, but yeah, with different APIs?
Right. Yeah, that's a really, really good question, and I don't know. But yeah, you're right. There is this feeling of, each thing is sort of this completely ad hoc solution to a specific set of constraints. Yeah, that's a really cool question. I don't know the answer to that.
So it's interesting because, you and Chris Okazaki, I would say, you're the two people in the world, probably, who know most about this. So I guess this is for everyone else. Here's a fertile area for PhD students, I think.
Yeah, right.
All right. Thank you, Brent. Let's thank Brent again.
All right. Thank you all.
Okay. Thank you for attending this session, and thank you to all the speakers for your wonderful presentations.